Let's give the greatest round of applause for the outstanding Casey Muratori.
So, in 1974, if you were a member of the Association of Computing Machinery and you paid the exorbitant subscription fee, or your institution paid it for you, you would receive one of these periodicals, and they came every so often. This one is volume 6. It came out in around December. And if you opened it up and looked at the table of contents, I don't know exactly what they would have thought at the time, but when we look back at it now, it's kind of like an all-star cast in just this one random issue of the periodical. At top there, very first one, the article's headlined by Ivan Sutherland, the creator of Sketchpad, who, if you saw last year's talk, was kind of an absolutely amazing creation, and he's considered one of the fathers of computer graphics. The sort of notorious Dragon book, if you will, the lead author of that, Alfred Aho, was talking about LR parsing in this article. Nicholas Wirth, the creator of Pascal, had an article on the composition of programs. And the K in K&R, Brian Kernighan, he had an article on structures of programs as well. But nobody really talks about any of these articles today. If you're maybe doing something specific, like where this article would be appropriate or something like that, then you might know about one of those articles. But there's one article right here called Structured Programming with Goto Statements by Donald Knuth that is still often referenced today. It's the only one from this periodical that pretty much everyone here knows, whether they know it or not. And the reason for that is because this article, again written by Donald Knuth, who of course is, world-famous computer scientist. His publications at this point are massive, but of course the most famous one is The Art of Computer Programming, which is a standard on programmers' bookshelves everywhere. And he had actually released one of these volumes before publishing this article, so very well known even at the time. In this article, which is huge, it's 40 pages long and has tons of sections. It talks about all sorts of things in there. It's very, very diverse. But no one talks about any of those sections either, just like they don't talk about any of the things in the periodical. They only talk about one section, which is the section on efficiency up there, that little tiny bit, and they don't really talk about most of it. They just talk about that part right there. And that's because that's where premature optimization is the root of all evil was first given like a worked example. Now, this phrase wasn't necessarily said for the first time here, but it's the first example that we have going back where premature optimization is the root of all evil is used in the context of something we can actually look at. Meaning there's an example given, there's a context for it. It's not just something people are saying, it's something they're actually doing. And so this phrase obviously has caused a lot of issues for people who work with performance and who, have trouble when they're trying to convince people that you need to take a performance into account when you're planning software, that it kind of always matters as something that you should think about. Because of course, the phrase premature optimization is the root of all evil kind of seems like it's sort of saying that you kind of want to defer these sorts of things, till really as long as you can. And it's ambiguous, sure, but that's kind of how it's taken oftentimes. And boy, did this phrase catch on. You can kind of see here, this is a Google Ngrams plot, so it's by percentage, which is not really the best thing, because you see this huge jump, which, that could just be because there's a lot more programming books being printed, so we're taking up more of sort of the published space as we become more of a discipline. But you can see, like, right in the 1974 era right there, it starts to become fairly common, whereas it was completely unheard of before that, effectively. And then it comes up to, very large compared to the total. Now, obviously, computer books don't encompass a huge percentage to begin with, and optimization topics don't either, but it's kind of remarkable when you look at the graph. So what happened was premature optimization is the root of all evil, something that I had certainly heard, and it's something that I kind of often had to contend with whenever I was talking about performance stuff. And at some point, I kind of realized that I don't really know what it means. I was like, I can make arguments against it that are kind of coming from like a hypothetical standpoint, or I can kind of, I could even make arguments for it, or say like when this actually does make sense as a rule of thumb that you should be thinking about and what that means. But really what I was doing was I was taking the phrase and just unpacking it to my like own experience. I was just kind of like saying, well, what does this mean to me and the things that I've seen, and making it mean what I wanted it to mean, which is actually what everyone does with the phrase. And so what I wanted to do, this was about 2 years ago, I wanted to actually go figure out what did it actually mean to the people who started saying it? Like, what was the real context? What was really going on at the time? So I could have that kind of understanding that you only get by knowing the whole story. So, ladies and gentlemen, welcome to the Better Software Conference 2026. My name is Casey Muratori, and I hope you will join me as we explore the root of all evil. And to start with, I want to talk about something that is not really important to the talk at all, but I know it will come up if I don't address it. And that is, who actually is the originator of this phrase? And it turns out that even though we know very clearly that Donald Knuth wrote it in 1974, and we have that example that's very clear, we also know that he wrote it again in 1989. Again, in the context of an example, not in a speech or not just like off the cuff, but actually in a publication. And that was a publication called The Errors of Tech. And in that particular article, he's talking about all of the bugs that were in tech when he was doing his initial debugging round. It's really actually a pretty cool paper because he kept a log. He wanted to know like what kinds of bugs people typically have, and especially himself. And so he kept a log of like, here's all the debugging that I had to do so I can go back and analyze it later. It's a very academic perspective, and I love that idea. But anyway, in this paper, again, it's huge, right? It's almost 80 pages long, I think. And it's just that one page is the only place where this is really talked about. And it looks like this, and what he's basically talking about is just this assignment to a variable that he removed to sort of save some time, but it turned out that not initializing it kind of bit him later when he made a change to the routine. So really, we wouldn't care too much about this other than like a little more evidence of maybe what he means by it, but the problem is, in there he also says, well, look, I also knew and forgot Hoare's dictum that premature optimization is the root of all evil in programming. So this time, he kind of said, he did us a little favor. Now it's not the root of all evil for all of humanity. It's just, the root of all evil for programming. So I appreciate that, but the problem with this is he calls it Hoare's dictum. Now, Charles Anthony Richard Hoare, or Tony Hoare as he was called at the time, is another sort of founding father of computer science, if you will. And so the fact that he calls it Hoare's dictum made people think, well, maybe it wasn't really Donald Knuth who was the one who kind of promulgated this. Maybe Donald Knuth kind of downstream of Tony Hoare having said it. So maybe it's really his idea or his thing that he was pushing, and Donald Knuth just picked it up. But the problem is, people have talked with him about it since. There's a phone conversation with Rico Mariani. I actually know Rico Mariani. He works on performance for a living, actually. And he was working at Microsoft Research at the time, and when he wanted to ask this question, and Tony Hoare happened to also work there. So he asked him, and Tony Hoare said, "It sounds like me, and I'm sure I could find the original source given a few hours in a good research library." So he was kind of like, well, maybe I did say that. Maybe it did come from me. I'm not sure, right? But then a year before that, actually the opposite was said by Tony Hoare in private correspondence with Hans Gurwitz, a completely different person. And he said, "I'm sorry, I have no recollection how this quotation came about. I might have attributed it to Edgar Dijkstra." And so the problem here is that we effectively have this, confusion about the origin, where we know that Donald Knuth wrote it in 1974. We know that he attributed it to C.A.R. Hoare in 1989. We know that Edgar Dijkstra is mentioned as a possible source in 2004 by C.A.R. Hoare, but none of those things is definite except the Knuth publications. And Edgar Dijkstra, unfortunately, passed away in 2002. He's actually the oldest of these three. And so no one can ask him if he actually was someone who said this phrase. So we kind of have this meme going on a little bit, like it's unfortunate, but that's the case. I think most people don't really think there's all that much of a dispute. It's just kind of unnecessary confusion. I think most people do think it comes from Donald Knuth. But the good news for this talk is it doesn't matter. Because if you actually go back and look at the history of how that article, Structured Programming with Go-To Statements, actually came about, then all three of these people are critical anyway. So you kind of have to know exactly what they were all doing and what their mentality was at the time and why they were doing what they were doing in order to understand where the article comes from that first uses it. So even if it wasn't Donald Knuth who kind of originally came up with this phrase, the other people who have been possibly mentioned are critical to the story anyway. So these three are the people that we're going to be talking about today. And they were all born like 8 years apart. So they're pretty close. They're pretty contemporaneous with the work they did. They all started programming as near as I could find. Don't quote that as fact. I just had to do digging to try and figure out when they maybe first started programming. And I would mention that the 1952 for Edsger Dijkstra, it sounded to me, when listening to the things he said in like his oral histories and interviews and stuff like that, it sounded to me like when he started programming didn't actually involve running it on anything. Like, they didn't necessarily have access to a computer when he was working on it. Not that computers didn't exist necessarily, but just he didn't have access to them. So programming was sort of more of a theoretical thing that you were doing, and you didn't actually run it. So that's how long ago that actually is in time. It'd be ridiculous to think about that today as something someone would have to do, like they could never run their program, right? So they all start programming kind of at similar ages. And again, that's because you weren't going to have a home computer when computers took up an entire room, right? They all are Turing Award recipients. And the Turing Award is, it's the highest honor we have in computer science, right? And they all won the Turing Award within 8 years of each other as well. And then the other thing that I'd mention, just because since I can't give you the entire history of each person here, I just thought this was kind of a wacky thing. They all very early on wrote Algol compilers. This was like a thing they all had in common. In fact, Edsger Dijkstra is credited as writing the first Algol compiler ever, and of course he was the oldest, so I guess maybe he was ready to tackle that first. But so I want to start with Edsger Dijkstra because he's the one who really sort of precipitates this. If he hadn't done what he did, it's unclear that things would have played out the way they played out. Now, it's not that his ideas were the only way the stuff that happened was going to happen, but it certainly wouldn't have happened the way it did without him. And I'm going to start with the thing that you know about, and I know you know about it because it still comes up on Twitter. It comes up on Twitter. Here we go, Linux kernels, go-to statements revive Dijkstra's famous debate. It comes up on Twitter because people are talking about this idea that go-to is considered harmful, right? So I want to start at that incident. You all know it, and it actually is crucial to this story. What happened was there was an ACM symposium on operating systems principles, and it was in the US. It was in Tennessee in 1967, and Edsger Dijkstra actually had a paper. It was called The Structure of the Multi-Programming System. And it's not like, like a band name or something like that. It's just that THE was a abbreviation that probably went with the university, right? And I don't speak Dutch, so I couldn't actually tell you exactly how it probably worked. But he was presenting this paper, and this paper was a report of things that he and his team at the university had done which were seminal in the field of distributed computing. They had written this operating system, and they'd written it kind of from first principles. And again, this is very early on in 1967. It's not like there's tons of operating systems and the things are all well known. And just to give you some context, here is a quote in 2022 by Butler Lampson, who is also a Turing Award winner, and specifically a Turing Award winner in the field of distributed computing. So somebody who's very aware of all the scholarship on the subject. And the way he describes it is, says he's presented a paper on the system which became an instant classic. Together with earlier papers, it introduced the ideas of sequential processes, non-determinism, mutual exclusion, and producer-consumer synchronization that are still the basis for concurrent programming today. So many of the things that we would still use or still just take for granted is like, oh yeah, these are things that if you want to run multiple processes at the same time, multiple cores at the same time, all those sorts of things, they came up with a lot of this. That's what they were actually doing at the time, was figuring out how to do that. And so the way that Dijkstra explains this is he was there presenting this paper. It's not supposed to have anything to do with go-to statements. Go-to statements are not on the menu. It's an operating systems conference, right? And he says he was sitting outside and talking to people, Brian Randell and others. These are, again, other people who you'll see come up often throughout this thing. He was talking to them, and he was kind of giving an impromptu discussion of things about GoTo that made it unsatisfactory. He started saying, like, there are some reasons why I don't think GoTo is a good idea. Here is an example of one of them. And the people who were listening was all like, this is great. You really should publish this. And so that's exactly what Edsger Dijkstra did. He said, okay, I'll write it up. he wrote up a thing called a case against the go-to statement, and he sent that to Communications of the ACM. And Communications of the ACM is like a very popular publication. You'll see it come up a lot in the citations as well. And this is what it actually looked like, a case against the go-to statement, and here's what he's talking about. This is the way it appeared in Edgar Dijkstra's actual manuscripts, if you look at them. But because when the editor of the Communications of the ACM actually received it, they were like, I want to get this out as soon as possible. They're like, maybe we don't do this as an article, so it won't have to go through like any kind of review process or whatever. We'll just make it a letter to the editor. We'll just make it like you're going to write into the thing. You wanted to say some stuff about GoTo. And the editor actually changes the name. And that quote there is how Edgar Dijkstra called it. That's not exactly the title. The title they change it to is GoTo Statement Considered Harmful, right? And so the problem here, of course, is, I mean, nowadays, I think, when we're all on social media, that still doesn't seem that harsh. Like, GoTo statement considered harmful doesn't seem all that violent of a statement, really. Like, okay, whatever. But I get the sense that back then, this was a lot harsher than a case against the GoTo statement, which just kind of sounds like you're making the suggestion that maybe it's not the best thing. And it turns out the editor who made that change was actually Nicholas Wirth, the creator of Pascal, who was editing at the time and who was in that periodical that we started with, right? And so he basically clickbaited everybody. He changed the heading, the headline of this article to something that was kind of much more inciting than it might otherwise have been. And of course, by putting Edgar Dijkstra right at the beginning, it's sort of like saying Edgar Dijkstra is saying that go-tos are harmful, and people hated this, right? And this is weird because Dijkstra didn't actually claim to be all that dogmatical about the go-to statement. He says that, people are making a religion out of it, and that's not what it is. I was just trying to give examples of how this wasn't necessarily something we should be using the way that we're using it all the time. And also, it wasn't necessarily just him. Like, he wasn't just coming out and saying, I think go-to statements are bad, and I'm the only person who's saying that. People had been saying that for a while, and in fact, there are people in the actual article that we're going to get to, that's the one that contains premature optimization is the root of all evil. Donald Knuth actually walks through some of them, and he talks about D.V. Shore at UCLA, who has been trying to not use go-to statements since 1960. And this article is published in 1968. So for 8 years, people had already been saying, maybe we shouldn't be making go-to be like the fundamental primitive that we're always using. Let's try to do something else, right? So it's not even really a new thing. Nonetheless, much like Twitter drama today, Dijkstra received a bunch of abusive letters because of this, and I don't actually have any specific of those letters. I never found when I was going through this like a specific letter where someone was hating on him, but that apparently is what he said happened. So this is not great for Dijkstra, obviously. No one wants to receive abusive letters, but it's actually a much worse time for him for other reasons. So in 1968, he is at the Eindhoven University of Technology, which is where he did that THE paperwork and all of the stuff that he had been doing. He's in the Department of Mathematics. And he literally writes that he suffered from a deep depression in this year. And he said there were 2 reasons for it. The first one was because they had done all this work, and the reward they got for doing this, seminal paper, basically, right? And all the things that they'd done up to then was that their group of people who had done the programming work were just disbanded by the department. And he doesn't exactly say why, but it's the suggestion that it's because the Department of Mathematics doesn't really take computer science seriously. They called it informatics, but it was basically, this is not really math, what you're doing here, and we don't really want you to keep doing this. And this is ridiculous because, again, this paper is something that's really, really important to computer science. And if you go and look at the actual paper, he talks about the conditions they had to work under to do it. And he said that he had very limited resources, 6 people. He lists the 5 collaborators there. And those were the people that, like this team that he built up. And it wasn't even like they were doing it full time, right? So they were kind of having to do this in a very makeshift way, and it got disbanded. And again, they did amazing work that future Turing Award winners said were like the basis of concurrent programming. And so I can only imagine how depressing that is to pour your heart into something and end up succeeding really at what you were trying to do, and then just be told, like this is not, we don't want you to do this here, right? So that's the first thing The second thing that was depressing to him was that he didn't really know what he should be doing. This group got disbanded. He wasn't really sure what he should try to do next. He just didn't really have any direction, so it felt kind of aimless. But he did feel like there was a pressing need to do something. And the something is kind of hard. It's a little bit hard to imagine at this time, but it's probably something that you can relate to if you kind of move it to more current events. And that's something that Dijkstra would later call the software crisis. And the software crisis was this thing that was happening in the 60s as computer hardware was becoming more capable. Effectively, what was going on was the old school programming practices, which were basically just like, I don't know, we have to sit down and figure out some way to fit a compiler in like 4K of memory, and we're going to have to hand code the whole thing in assembly language, and we're just going to have to use all these tricks to get it to work at all. That model of programming wasn't really going to scale, especially not with the number of programmers they had and the resources they had. That wasn't going to scale to the kinds of applications that the computer hardware could do as it was getting more and more powerful. And so the way Dijkstra described it is that hardware is rushing ahead of programmability, and unless something drastic happens, the situation will only get worse and worse. Little did he know. He lists some things that he observes, and they're kind of in Dijkstra-ese, so I'm not sure we can impact them completely. But I do like unstructured multitude and bigness, chaos, unreliability, and unadaptability. He's kind of got these things that he's thinking about, these like demons that need conquering. And his goal in his head for computer science was that what they need to do is regain control over this process, to have some way of actually feeling like they were going to be able to make programming a real discipline where it wasn't just completely ad hoc, and you could actually have some feeling that you were going to succeed if you did a particular process, right? Now, later on, when he recalls this era, he says that to talk about software crisis at that time was blasphemy. And this was another part, I think, of the Depression, although he doesn't come right out and say it. And that was basically that he felt like he was the only person thinking this. Like, other people weren't admitting that this was a problem. They were just like, software is fine, it's great, it's perfect, it's way better than it's ever been. We're all very happy. I don't know what your problem is, dude. And he gives this example where he says, the prevailing culture characterized by the 1968 IBM advertisement in Datamation that presented in full color a beaming Susie Mayer, which he, I think, misremembered the name, but we'll get to that in a second, who has solved all her programming problems by switching to PL1. And the first time I read this kind of a thing in one of Dijkstra's publications, I was like, okay, I don't know what that is. It's just some offhand comment. But I saw it come up. He says it multiple times. Like, this really stuck in his craw, I guess. And I thought maybe, well, I just don't know, maybe the Susie Mayer person is like a programmer at the time who was just like a spokesperson for IBM or something like that, and he was angry about it because he thought that her suggesting that all the problems had been solved was ridiculous and counterproductive or something. I just didn't know. So I was like, well, I should probably go dumpster diving for this, right? So I started reading through Datamation magazine, because like all the back issues are digitized. And he said it was in 1968, so I concentrated around there, and I just read through like each and every one of those things until I could find something that I thought must have been the ad that he was talking about, and I believe I found it. It's Susie Mayer, not Meyer. And she doesn't actually exist. She's just a fictional construct made up by IBM to sell their new language they're promulgating, which is PL1. And the puff text for this PL1 is really something. It starts with, can a young girl with no previous programming experience find happiness handling both commercial and scientific applications without resorting to an assembler language, right? I don't know. Can they? And the other thing it says, there's two other things it says. With PL1, programmers don't have to learn other high-level languages. They can concentrate more on the job, less on the language, and that the language provides a new ease of writing. It's neither cryptic nor verbose. It sounds like vibe coding, right? It sounds like the next thing that they're going to do is tell you, like, look, we got this thing where you can just type in English what you want, and the AI generates it for you, and it's going to be great, right? I mean, that's kind of what it sounds like they're going to pitch, and I know it can't be that because this is in the 1960s. And so I was like, well, I want to see what this PL1 actually looks like. So it turns out that's the October issue of Datamation that Susie Mayer advertisement appears in, and the November edition doesn't have PL1 in it. The December edition happens to be all about PL1. You can see like the PL1 there kind of on the cover. So it's like, awesome, same magazine, contemporaneous reference. I can actually just look at what IBM was thinking they were providing that's like as good as just typing an English sentence to an AI and having it generate your code for you without you knowing anything about it. And this issue has several articles on PL1 there at the top. I'll just pick one of them because it had the best examples, and that is PL1 for command and control, military command and control. I like that in the corner it says not yet, which doesn't seem to bode well for PL1, if I'm honest about it, but let's take a look. You guys can be the judge if you think that this is good enough for Susie Mayer with no programming experience to just hop in here and get to work on scientific applications. That's what it looks like. Not exactly vibe coding, if you ask me. It seems like you're going to have to know quite a bit about programming to make sense of something like that. But the part that I thought was really great is the author of the article was kind of lamenting a bit, and he's saying, well, let's suppose that I just have a data structure that's like 32 bits, and I want the first bit to tell me whether the thing that's stored in it is going to be 5 bits or 8 bits, right? I just want basically a discriminated union, like a 1-bit discriminated union, where I can read the top bit and know what I'm getting. Well, that thing on the side there is how you would declare it. I've color-coded it for you. So the discriminator bit basically is the blue, the 8-bit is the green, and the 5-bit is the red. And this is what you would have had to have typed in to create that data structure. And if you look at it, you can understand why that does describe it. But it's kind of ridiculous that you would have to type all that in. You know, it's really far from like no programming experience necessary, and you'll just hop in here, right? And by the way, all of those nulls are necessary. You had to have all of those nulls in there, and they had to be uniquely named if they were at the same level, even though they're nulls, so you can't refer to them anyway. So that's the kind of language that we're talking about. And what I can say is, I do think I now know why they did this shot, is because that, presumably, is her holding some probably relatively simple data description, and it just took like 50 pages or something to get through because you handed this poor person PL1 and asked them to write something in it, right? Now, the other thing I'll point out here, because this is important to understand like the timing of all of this, is that there's no, do you see a computer? It's not funny. Don't laugh, because there wouldn't have been one. That's what you have to understand about this era. There wouldn't have been a computer. There's just punch cards, which I believe is what she's holding there, although the picture isn't great. Punch cards, print out listings of the thing, and a desk where you sit with a pencil and figure out what you're going to code. That is something you would have been doing in 1960s in a lot of places. And so, focus in here, you get a phone and you get a lamp, and you write the rest of the code. That's how it works. Now, it's really interesting. I want to hammer this point home because this is pretty important. The stuff that we're talking about, the article that we're talking about, is published in 1974, which isn't much later. It's only 6 years after this. And if you look at the way like Dijkstra and Knuth talk about this era, I pulled some quotes for you just to really underscore this. It's just not just Susie Mayer who has to do this. It's everybody, right? And Dijkstra is hypothesizing in this very year. He's sort of thinking, what might it look like if I had a text editor, right? Like he's just imagining what if we had a text editor. And he says, we may expect that computers will become more directly accessible for the individual user, and we may expect that the latter should like to use capabilities for the text manipulations involved in program composition. At present, I'm rather unsure about the true nature of the text manipulations the user would then like to perform. It is certainly something more structured than just deletion and insertion of characters or lines. So that's all, he's kind of like imagining, you know, it's probably going to be some cool stuff we can do with this, but I don't know, because I don't have the luxury of having one of those. Same thing with Donald Knuth. Later on, 1973, he actually writes, perhaps the new display terminals, like, you know, the new ability to actually see something that's going on. The new display terminals will provide the answer as a notation for programs that will provide an appropriate reflection of the structure as we might have it in our minds. And he then describes a system by which you could basically jump to definition. something that we all expect to be able to do today. Knuth was like, oh, you might be able to like take a function and expand it to what the function body was. That would be baller, right? So you have to appreciate what they were working with. I mean, the reason that all of these people are founding figures in the computer science field is because they were working with next to nothing and had to come up with everything. So anyway, Dijkstra is depressed, and he kind of wants to get himself out of it, as you would. And he starts to think to himself, when I think back on this, I kind of knew that Algol, the thing when I'd written the Algol compiler, and then that THE multiprogramming system, I kind of knew that they were these, I don't know, like training exercises, basically. He calls them agility exercises, where they're just kind of getting me ready to really do something cool. Which is crazy because those two things were really cool, right? Like they were things that very few people could have accomplished at that time. The only other people who would do something like that are other Turing Award winners, right? And so he was thinking, those are going to be training exercises for me to go do something really awesome. Like I'm going to go do something very impactful now. And he doesn't really do this on his own. He says that there's a turning point in this sort of depression and this desire to move forward but not really be able to do it. When he goes to a software conference, it's basically a NATO conference on software engineering in Garmisch, Germany. And this is in 1968, so it's during his depression. And he says that at that conference, it was the first time where he felt like people were actually kind of on his side, where he felt like people were kind of coming around to the idea that there was a software crisis, and he didn't know that people had those thoughts. Kind of like stopping feeling so isolated because he met other people who were thinking like he was. So what happened at this conference? Well, this is what it looked like. We actually have pictures from it, which I think is so cool. And I'm just going to go ahead and give the picture credit now. There's a fantastic photo series that's posted by Brian Randell, who you heard about earlier, and Robert McClure, another programmer from the era, that actually took pictures and digitized them. And thank you so much for doing this, because it's so cool to be able to see what it actually was like. There are not that many photographs that are digitized from this era that you can look at, seeing them doing the sorts of things they were doing. So that's Edgar Dijkstra right there. That's him, and they're standing around chatting. This is him in an actual conference there, right? This is in the actual discussion room. And he's got two papers that he's presented, two working papers that he's presenting at this conference, but that's really not the thing that makes him feel good about the situation. It's actually just the attitude of the other participants. And specifically, I can't really capture the entire thing. You can go read this entire report. It's actually huge. You can get more of a flavor of it. But I'm just going to try to give you an extract to give you a feeling of sort of why he then started to think like, oh, this is really good. This is like actually people are taking this seriously, and they're very smart people who are taking this seriously. So in session 7, which was called Special Topics, there was actually, this is from the editors who kind of described the situation after the fact when they were writing up the report. They said, quite early in the conference, statements of concern were made by several members about the tendency for there to be a gap, sometimes a rather large gap, between what was hoped for from a complex software system and what was typically achieved. And the opening sort of salvo was a position paper, because there was a position paper presented as part of this special topic section. This man right there, actually, who was one of the co-authors of the position paper, he actually almost shows up in the big oops. He almost shows up. And the reason he doesn't show up is because if you remember this slide from the big oops, where I was talking about the fact that Bjarne Stroustrup was the reason that we have strong function prototyping in C, not in C++, but actually in C, it was work that he did that made that happen. For brevity, I omitted the rest of the quote from Stroustrup. The rest of the quote read, "To get conversions, period, the idea of square root 2 not being a valid program was just not acceptable. That can't happen. I was complaining a bit about that, about C. And Sandy Fraser said, why don't you just fix it? So I did." Sandy Fraser, who is A.G. Fraser, I don't know if it's pronounced Fraser or Fraser, I could not find a definitive answer to that. But Sandy Fraser was actually his boss at the time. It was Bjarne Stroustrup's boss at Bell Labs. And he was the one who said, you know what? Why don't you just go fix the C prototyping? Just do it, man, and then we won't have to deal with it anymore. So he almost came up, but because we didn't follow his path, he didn't get to be in there. But he's in there now, and so now he And E.E. David, who is from Bell Labs. Sandy Fraser was at this time still at university. He wasn't studying at university. He was a professor there. But E.E. David was at Bell Labs, and the two of them had written a position paper where they talked about this software problem, and it was part of the things that presented right at the beginning of that session 7. And what they say is there is a widening gap between ambitions and achievements in software engineering. This gap appears in several dimensions, between promises to users and performance achieved by software, between what seems to be ultimately possible and what is achievable now, and between estimates of software costs and expenditures. The gap is arising at a time when the consequences of software failure in all its aspects are becoming increasingly serious. For example, particularly alarming is the seemingly unavoidable fallibility of large software, since a malfunction in an advanced hardware software system can be a matter of life and death, not only for individuals, but also for vehicles carrying hundreds of people, and ultimately for nations as well. And again, these fears were well-founded, as anyone who knows history can attest. Now, there were some people who weren't as gung-ho. Kenneth Collins, who's from Boole and Babbage, a company from California, was like, okay, guys, let's tone it down a little bit here. I don't like the word crisis. I feel like that's a little bit much. We're not really in a crisis. The only problem is that things are expanding, and we're just a little bit beyond our theories right now. So it's not a crisis. It's just, something we're going to deal with. But the temperature was not going to be turned down. And the reason the temperature was not going to be turned down is in this photo right here. And I don't know if you can see it because it's, not that high resolution. But this right here, ladies and gentlemen, and I have a better picture from a different part of the conference, that right there, do you recognize this face? People who were here last year should recognize that face. Do you recognize this slide from last year's presentation? That is none other than Douglas T. Ross, the man who created the Plex. Now, you may be asking, is he bringing his big Plex energy to this particular conference as well? And the answer is absolutely. In session 5, he actually talks about Plexes, and he introduces the concept and all that sort of stuff. So he was definitely Plexing, but he also wasn't having any of this Kenneth Collins stuff. He was like, okay, Kenneth Collins says there are many areas where there is no such thing as a crisis. Sort routines, payroll applications, for example. It is large systems that are encountering great difficulties. And Doug Ross was like, no, man. It makes no difference if my legs, arms, brain, and digestive tract are in fine working condition if I'm at the moment suffering from a heart attack. I'm still very much in a crisis. So really, this is sort of like a cameo from the previous talk, but I absolutely love the fact that in this particular case, Doug Ross had Dijkstra's back 100%. Anyway, A.G. Fraser closes out by saying, we are making great progress, but nevertheless the demands of the industry as a whole seem to be going ahead a good deal faster than our progress. We must admit this, even though such an admission is difficult. And that leads Edgar Dijkstra. It is actually a transcription from something he said at the conference at that time. This entire thing is like an exchange that's transcribed in the record. He says, the general admission of the existence of the software failure in this group of responsible people is the most refreshing experience I have had in a number of years, because the admission of shortcoming is the primary condition for improvement. So he basically thinks of this as, this could be a turning point. Like this, if all of these smart people are actually as concerned about this as I am, then we are in good shape. So, still tough to get out of the depression, but he starts. He's like, all right, in my depressed state, it took me months to gather the courage to write for therapeutic reasons. He numbered his monographs, so he like those papers, they each kind of get a serial number. EWD 249, Notes on Structured Programming, which is what comes out of this. And in August 1969, which is not quite a year later from the conference, he writes it up. He finishes writing it up. And he says that marked the beginning of his recovery. And this is what it looked like. This is what his monograph looked like. Now, it's kind of tough for me to describe what's in this, because it's fairly wide-ranging and has a lot of different parts to it. Notes on Structured Programming is sort of like, it's almost like several mini papers, and what's like a collection of short stories in the fiction world would be, I would say. And so what I want to do is, I know it's a little confusing, but I think actually the easiest way to understand it is for me to just talk about sort of a precursor to it, because you can kind of understand Dijkstra's mindset, and most of the things that he talks about in that Notes on Structured Programming, you can understand them if you just think about this one example and imagine lots of things along these same lines. So what Edgar Dijkstra wanted was a way that you could take programs and, rather than looking at them from the perspective of, I write a program, and then if I want to know if it works properly, I make a proof for the program. Like I make a formal proof for the program after the fact. What he wanted is a way to go the other direction. Basically, I make the proof either ahead of time or at the same time as the program. So the idea is sort of the process of making the program is also the process of making the proof. And the way that he describes this in various ways at various times, they're all kind of illustrated by this example that he gives in this precursor to Notes on Structured Programming. What he does is he does a form of what we would consider top-down programming, but it's got some important subtleties to it that make it not the same as probably what you and I would necessarily think of as top-down programming. And what he does is he first sketches, like you would in a top-down program, he says, like, what am I going to do? In this example, he's doing a producer-consumer pattern, so you've got a producer that's making stuff, a consumer that's consuming it. And he just writes down like, okay, here's what I imagine the producer would do, the things that it would do, here's what I imagine the consumer would do. And then the difference between top-down programming and the kind of things that he's thinking about is top-down programming, we then just go start implementing this. Like, oh, I'll go start implementing P1, like I'll write out how the producer is going to produce, and if that, maybe I do the same process at that level and I write some things down. It's not exactly that. What he says is, what I now do is I think about what is something that, given this initial sketch, has to be true. Like, what has to be true about this system in order for it to work? And then I'm just going to take that one thing that I know has to be true, and I'm going to update the program to incorporate that one thing, to remove the ambiguity about that thing. And so here's his example of like step 2 here. What he's done is decided that there has to be some number in which, or sorry, I should say variable. In this case, he represents it by n, which says how much has been produced or consumed in these cases, right? Because he's like, I have to track that information, and I know that it has to get bigger when I produce something and smaller when I consume it, right? And so again, it's not exactly top-down programming because he's not expanding a particular thing. He's just putting in one constraint that he thinks he knows has to be true. And he just repeats this process. He repeats this process until he gets to the program. And in his mind, this is sort of the way that programming should be constructed. Later, he starts to call it stepwise program construction. And the idea is that if you do it this way, then you basically get an informal proof that the thing had to be this way and would work properly because at each level, you kind of had this idea about what had to be true about it, and that thing that had to be true is encoded in the program. And he's very clear. He doesn't make any pretenses that these are formal verification methods. He just sort of says, like, look, rather than ad hoc programming, this is the method that I follow, and it allows me to make programs that are going to be like a lot more, I can be a lot more convinced that they work properly if I do it this way. Okay, there's a lot more in Notes on Structured Programming, but you could do a whole lecture on it. Anyway, there are Xerox machines already at this time, obviously. We can reproduce things. And so he says, thanks to the ubiquitous Xerox machine, this text spread everywhere. Like, people were really into it. And Dijkstra credits that to the fact that people found it refreshing in the popular culture. Again, the popular culture being like that IBM PL1 attitude that like all the problems are solved. I'm not so sure about that. I'm not so sure that's like why people actually found it or why they liked it, why they spread. When I read the paper and I think about the other sorts of things that were available at the time that people might have gotten, the thing that I think is actually remarkable about this paper is that it kind of reads like a Twitch programming stream. In the same way that like nowadays, it's very, very helpful to be able to see a established programmer watch what they're doing and go, oh, that's how they think through a problem. This paper, Notes on Structured Programming, actually feels a lot like that. It goes through and it sort of has this flow, and Dijkstra describes at each stage why he's doing what he's doing and how he's doing it, and a lot of people weren't writing like that. So here you have a very prominent figure who's already very accomplished. People know who he is, and they know he's very good. And he has this sort of presentation now that you can go look at that walks you through how he's thinking about code. I suspect that despite Dijkstra thinking it's just because of the prevailing culture, I think it's actually because this was probably a very good educational material for a lot of people for figuring out how someone who did some really great programs was actually thinking through the problems. So the next step in the chain to get to Donald Knuth's article now requires more of a team up. Now, this is from the Big Oops. This is a slide from the Big Oops. As we know, Doug T. Ross, creator of the Plex, passes it on to CAR Hoare, who does record handling, who passed on to Ole Johan Dahl and Kristen Nygaard, who were the inventors of, or creators, I should say, of Simula. I'm going to omit Ole Johan Dahl from this team up, and I'm sorry for doing it. I don't want to shortchange him. It's just that he already had a large chunk of the big oops, and all the things that I would cover are just the things that we covered last time. So I'm just going to talk, I guess I should apologize. I'm sorry, he's on the left there. I'm sorry for leaving you out. He's as important as everyone else for getting this book published, but I'm going to focus on Tony Hoare because he's one who didn't really get much in the previous lecture. So meanwhile, while all this stuff is happening with Dijkstra, in the UK, at a company called Elliott Brothers, it's kind of a division of, it's a large-ish company. It's not that big by computer industry standards, but it's largest, so it has some divisions. And Tony Hoare is actually working in the programming division there. And he's working with new computer systems that they make and trying to provide sort of system software for those computers. And in the 1960s, the early 1960s, he's working on, as I was foretold to you, he's working on ALGOL compilers. And in 1963, they actually ship their first ALGOL compiler, and they deliver it. It's a team of people. I believe Jill Pym is his future wife, so he was actually working on the compiler. It was a husband and wife team, although they weren't a husband and wife team yet, I don't think at that time. They shipped the first version of the ALGOL compiler, and this project goes pretty well. It's apparently a pretty good ALGOL compiler. Users like it. There's no complaints. And as a result of him working on this, sort of in the middle of that project, he gets asked to join the working group for ALGOL, for like the specification of the language, for like improving the language, because ALGOL, I think it was ALGOL 58 probably might have been one of the things that would have been moving forward, and then there's ALGOL 60, and they have all these like additions and revisions that they do for the thing. So anyway, he gets on the working group, and he starts working with people on thinking about like additions to the language. And this is really where the record handling stuff comes from. But during that same time, while he's on the working committee, they also are going to build a new set of system software, a new suite of system software. And so they've shipped this ALGOL compiler, and they're like, okay, that was successful. Now what we're going to do is we're going to ship like a whole software suite, right? We're going to launch this new computer, and we're going, well, it's not a completely new computer. They're going to launch like a new revision of a computer, I guess. And we're going to have this software suite called the Elliott 503 Mark II software system. Naming conventions were interesting back then. Anyway, and so he works on this system, and it gets very large. They had 30 people by the end of it, he says, and it was not going nearly as well as the first project. He says, after a while, it became apparent that the project is not going to succeed, certainly not in any foreseeable timescale, so he's concerned with trying to rescue it, like to try to like salvage this sort of really bad follow-up to what had been a successful project. And it had been going on for 2 years. They were like, what if we just cut this way back? Like, let's just try to really narrow the scope of what we're trying to deliver here. And is there something that we could actually get out in 6 months so we don't have absolutely nothing to give to our customers? And it did sort of work. After 6 months, they were able to get the very first piece of this software suite out, and that first piece was a new ALGOL compiler. But the problem was it was very slow. They had obviously shipped one previously, so they were kind of competing with themselves here. And they said that the first ALGOL compiler they'd shipped was around 1,000 characters, 500 and 1,000 characters per second on average. So between 500 and 1,000 is how fast this thing would go. And the new one was 2 characters per second. So not a good thing to have to go to tell customers, right? You know that thing that was like 500 to 1,000 characters before? Now it's 2. I hope you guys have a long time to wait for compiling your ALGOL programs, because even though programs were small back then, 2 characters per second is going to be pretty stiff, certainly. So I was reading this, and I was like, well, maybe it's just a typo, because it doesn't seem real that you could get down to 2 characters per second if you previously were doing it at 1,000. Like, I'm totally willing to believe that maybe it requires 2 per second because the hardware was so primitive and ALGOL was so complicated or something like that. But it's weird that they already had done one that was operating between 500 and 1,000, and now they got down to 2. And when you read these papers, they like the scans often look like this, so they're kind of, they look kind of janky. And this happened to be from an actual transcription of a conference. So I'm like, maybe they just wrote it down wrong. Maybe they meant like 200 characters per second, because that would be just like, okay, yeah, we didn't do as good a job, or maybe it's got some more features, and we just couldn't manage the complexity or something, so we couldn't hit the old target, but it's not awful. Well, it continues and says a very considerable amount of additional work was expended to see why it was so slow and what measures should be done to improve it. It was very difficult, but after a few months, we managed to speed up the compiler to 8 characters per second. Oh, sorry. 8 characters per second, which is a big speed improvement, to be fair, right? It's a factor of 4. So you can go to your boss and be like, great news, I got it 4 times faster. Unfortunately, it's still 8 characters per second, which isn't necessarily fantastic. After that, the project was canceled. That was it. They were like, we're not going to be able to do anything with this. It's over. Let's just regroup, reset, and we'll start a new project. And later on in his Turing Award lecture, which was in 1980, he actually recounts this and gives more details. And he says the same statistics, so it turns out it was not a misprint or a double misprint or anything like that. It really did go down to 2 per second. And he gives some explanations for why. He said it turned out that we'd failed to make overall plans for the allocation of main storage. Everybody who wrote their own separate pieces just kind of assumed that there would be some kind of magical allocator or overlay that would take care of this for them. And so nobody had figured out, like where's this stuff going to get stored? And furthermore, they didn't know even like that. They didn't think about the fact that the user program would have to be there as well. Like the users would need to they want to run their programs, and the stuff that that they had written was taking up all of the main store to begin with. So they hadn't counted for that at all. He also then, says as they started to troubleshoot it, they were finding that really what was happening is because of this sort of failure to manage memory, it was basically VM thrashing. Like the fact that they had to do all these sort of gyrations to then figure out how to get the memory to work meant that they were swapping between sort of the fast core and the slow parts of the system. So it was literally just like VM paging that they were hitting, which is what slowed things down so dramatically. Now, he takes this lesson and he feels like afterwards they actually are able to deliver some pretty good software. He says, in the end, I think the experience led to very much improved design of software. From this disastrous episode, the reputation of the software team did recover and the products are now in successful use. So he felt like this was a good learning experience. Obviously, the project was a disaster, but it didn't stay a disaster. Like he learned a lot from it, and institutionally they learned a lot from it, and they did make good things afterwards. So that's kind of his experience during the 60s and what he was working on. So one really good experience followed by one really bad experience that was fairly lengthy, unfortunately. So during the same time, he's working on Algol. Like I said, he's on that development committee. And he writes a paper with Nicholas Wirth, again, the creator of Pascal, and the person who clickbaited everyone in the GoTo paper, or I should say GoTo letter to the editor. He does a paper with him. And the reason that Tony Hoare and Nicholas Wirth are working together here is because, again, they're both trying to kind of move Algol forward. They want to try and make improvements to this language and make it better. And the way that Tony Hoare is contributing, there's a couple different ways, but the biggest one he does is he proposes basically putting the plexes, right, by putting this idea of structures, basically, into the Algol language as sort of first-class citizens. And again, we know that they got this from Doug T. Ross, not because it's me just reading into it, but literally in this paper, they credit Doug T. Ross as being the person who came up with this idea, like this Plex idea, that now CAR Hoare kind of renames to records rather than plexes. We would again now call them structures. Anyway, so Tony Hoare is big into this idea. I unfortunately have never found anything in his own words where he describes why he was so into this. There isn't like a thing where he says like, oh, I was hanging out with Doug Ross at this conference and he was talking about plexes and I got really into it and I thought it was cool so I went off and did it. Or I was working on this project and I tried using these things and they were awesome. There's like nothing I can find. So it's still kind of a mystery to me how he got on this sort of track. But he definitely gets on this track of thinking about this a lot, because he gives these sort of lectures at Dado Summer School, not just once, but multiple times. This is what it looks like the first time he gives it in 1966, but he also gives it again in like 1970. And probably in between as well, although I don't know all the documented times when he may have given this. So again, this is another kind of idea like the Dijkstra ideas in Notes on Structured Programming, where you kind of have this idea of looking at data and trying to bring it into a more managed form. Instead of just having storing arrays here and there, global variables, who knows what's going on, ad hoc usage of the main store or the ideas about where data is, records, plexes, structures, whatever you want to call them in the end, the idea is you're going to bring some order to that chaos, right? You're going to try and say, this is how we're going to structure things. And it does have levels of abstraction, just like Dijkstra's Notes on Structured Programming talked about this sort of starting at the top and like expanding down as you know things. Because right from the beginning, the record handling classes talked about things like subclassing, like saying, well, I've got this one type of record, and I might want to have versions of that have extra things in them. I might want to have a hierarchy of things, and so on and so forth. Now, things end for CI Horror in the private sector when the company, that Elliott Brothers company, it gets acquired. And it gets acquired, and then that was acquired by another acquisition. I like in this quote, I transcribed it verbatim, he says it was taken over by a longer company, which I don't know if that was a typo from the original transcriber, but I love the idea of companies being longer than each other as opposed to larger. So I'm leaving it in. I'm saying that's what was actually said. And so anyway, in this particular way, he found that there was nothing really left for him to do once they were acquired. He didn't think he was going to be useful anymore. So he decides to go to academia. It turned out that there was he saw a job opening basically where he could apply, and he does. And he ends up going to Queen's College, I believe, is the name of the place. So once he's in academia, he can interact more with other academics, not just on that working committee, but in general. And he goes to the IFIP working conference, or at least that's as well as he recalls. In 1972, it was on formal language definitions. So again, it makes sense that he's there because he's been working on ALGOL. That's kind of an area of interest for him and things like that. And he meets Dijkstra and Dahl there in his description for the first time. Now, there are conferences at which these people have been together in the past, but there isn't really a record of them actually interacting. It's like someone's in the audience and someone's giving a paper or stuff like that. So apparently this is the first time, at least according to Tony Hoare, and no one else really talks about it but him, where he met these two and actually had a conversation, and they kind of got some ideas going. They had some things in common. They were all working on sort of similar sorts of stuff, and they all had these projects they had been working on. Notes on Structured Programming for Dijkstra, the record handling stuff for Tony Hoare, and then the stuff that Dahl had been working on, Simula, that was covered in the Big Oops. And they think, maybe we'll put these together. Maybe we'll make these into a book, and this could be something that we could publish and sort of share with the world this idea of how to bring structure to these different aspects of things. And since he was an editor at Academic Press, he could naturally get it published because he could just be like, hey, I'm editing this series, and you know what? What if one of my new books is in this series? We can publish that as well. And that is how Structured Programming, the book, comes to be. And it is quite literally a collection of those three things that I almost walked you through. I didn't walk you through the Dahl one. And Hoare apparently kind of rewrote some of the Dahl one just to kind of make it flow better. I guess it sounds like, from Tony Hoare's description, I don't want to make it sound too harsh, but the way Hoare described it, it sounds like Dahl is maybe not the best writer for getting his point across, right? So Hoare is listed as a co-author there, but it's not really because he authored the ideas. It's because he kind of worked on the section. And what they form is talking about how to do abstraction and thinking through problems for three different types of things. The Dijkstra section from Notes on Structured Programming is about the code. The record handling section from Tony Hoare is about the data. And then the sort of object-oriented programming, so the part from Dahl, which was about Simula, is sort of about thinking of them together, right, as like object-oriented programming or the kinds of ideas that we talked about in the Big Oops. Now, you may ask, was this book a flop? Like, did anyone care about this? Because you've never heard anyone say, like, you've asked someone, like, what kind of programming you're doing, they're not gonna be like, oh, I'm structured programming. Like, I do a lot of structured programming. It doesn't seem like it's stuck, right? But I think after having read through this book, I would say that most of the ideas in it are ones that now we just do, right? So I would say that whether or not the book was the thing that made that happen, the ideas in the book, at least, are the ones that we now do, no matter what kind of programming you do. You're either doing the kind of record work that Tony Hoare is talking about, the kind of program breaking things down into different pieces that Dijkstra was talking about, or you're doing object-oriented programming like Dahl was talking about, but you're doing something probably multiple things from this book. So I think the reason that people don't say structured programming anymore is because it's just programming now. Like, in a way, the ideas in the book won so hard that they were forgotten, right? One of the worst things you can do if you want to be remembered for something is do it extraordinarily well, because then it just becomes part of what everyone does, and nobody really thinks about the fact that you did it, right? So programming with abstractions is probably the easiest way to talk about what that is, and this comes from actually a definition by Hoare himself. When Donald Knuth asked him, what is the sort of quick set, what's the elevator pitch for what structured programming is? He says it's the systematic use of abstractions to control a mass of detail and also a means of documentation which aids programming design. So that's his kind of capsule summary. So anyway, we've covered everything that gets us to that book, and now we just have to give the book to Donald Knuth, which happens in 1972 when the book is published. Ole Johan Dahl gives him a copy of this book, and what he does with it, like how we get from there to premature optimization is the root of all evil, is for after intermission. So let's go to Stanford University in California in 1969. And what I want to start with is these two fellows right here. Donald Knuth, obviously, is the reason we have structured programming with go-to statements, the article. Robert Floyd is sort of his longtime partner in crime. And they met at a conference. As you can kind of see, there's this theme of, the Turing Award winners and founders of computer science meeting at conferences and then going off and doing interesting things. And Bob Floyd is actually another Turing Award winner. We won't really be talking too much about him in this lecture. There's a ton of awesome things that he did on his own. But he and Donald Knuth meet at a conference, and they hit it off right away. They then kind of have this exchange where they're long distance correspondence. They write letters to each other where they talk about things that they're working on, and they sort of have a one-upsmanship kind of thing where they're talking about something or trying to prove something or trying to develop a theory, and someone will write, here's my idea, and then the other person will be like, oh, but have you thought of this? And then the person will write back, oh, yes, that's cool, but what about this? And so they kind of want to work together. And when Donald Knuth is trying to figure out where he's going to go, because in his mind what he wants to do is he wants to be a professor somewhere and just be a professor somewhere for like the rest of time, which actually is what happens, right? He ends up going to Stanford and he stays there forever. So he just wanted to do that one move. He didn't want to be someone who bounces around to a lot of different universities. So he and Bob Floyd were talking about where they wanted to go. Knuth said, I'm thinking Stanford is maybe my current top choice. Eventually, Robert Floyd is like, yeah, I think that would be the best place. And so they decide they're going to try to go there as like a package deal. So Knuth presents that to George Forsythe, who's one of the main people at Stanford at that time in computer science. It's like, what if we went there together? And Stanford's like, okay, you can totally do that. Well, you guys can come together, and you can both sort of open some new departments. If you go digging, you can find these research in the computer science department reports that Stanford University has. They're kind of in their tech report archive. If you're doing the kind of dumpster diving that I like to do, you'll find stuff like this, and you can kind of see what the department looked like on any particular year. And what you can see here is it's kind of like that periodical at the beginning. There's like a lot of computer science greats just listed as department heads. You've got John McCarthy, right? The creator of Lisp is the artificial intelligence lab. You've got George Danzig, who I don't know, probably not many of you have experience with operations research or optimization algorithms, but like the simplex algorithm, Danzig's algorithm, that's him. He's in the operation research department. So you kind of have a really stacked Stanford at this point. And Robert Floyd and Donald Knuth are going to add to it, and they have two departments that are proposed that they're going to be running: programming languages and analysis of algorithms. Now, analysis of algorithms is not really related to what we're going to be talking about here, because obviously, like structured programming with go-to statements, you can even kind of tell by the title, it's probably not a lot of, hardcore mathematical analysis of how the algorithms work, but programming languages, obviously that's right in the wheelhouse. So it's not really something that Donald Knuth is going to go, spelunking for. It's actually right in the wheelhouse of what he's supposed to be doing. And remember, that structured programming book is 1972. This is 1969 where they come to start these departments. And if you look at the computer science research report there, the sort of thing that lays out what the department is doing, you will see a description of the sorts of things that they were supposed to be working on. It says, in order to help find long-range solutions to the software problem, and you'll notice this is sort of the same as the software crisis, like everyone had their own name for it, but even right in the description of this department, it's being acknowledged that there's this problem. With software specifically, Professors Robert Floyd and Donald Knuth proposed to direct a series of investigations of important aspects of compiler writing and closely related subjects. The major unknown factor in contemporary compiler design is the lack of reliable data about what users do with programming languages, and it should be possible to estimate, for example, how much time is spent in various kinds of lexical and syntactical analysis. They kind of go on and on about all the things they could be doing to analyze what sorts of things people are doing in languages. And there's even like a 5-bullet point thing here where they kind of talk about stuff they could do. And all of it, again, is right in the wheelhouse of things like structured programming and structured programming with go-to statements. This idea that you're going to start to look at these languages, how people are using them, how can you improve the tools, how can you improve the compilers, how can you improve the way people make programs. Now, even before he gets the book, Knuth is into the structured programming idea because, as we've already seen, a lot of the pieces of this were already in motion. The notes on structured programming monograph was circulated by Xerox. Obviously, Knuth knows these guys. He corresponds with Dijkstra, all this sort of thing. So he's aware of this movement of structured programming. And he says that right from the beginning there in 1969, he and Robert Floyd were going to make that part of what they were looking at. They weren't like naysayers. They weren't people who were like, structured programming now, we're going to keep writing everything in assembly language, or we're still going to be using like just original Fortran or something like this. They weren't that way. They wanted to be on that sort of bandwagon, as he calls it. They wanted to be moving things forward in that same direction. And the way Donald Knuth describes his first experiences with structured programming, trying to do it himself, he says that in 1969, when he got to Stanford there, he was trying to teach introductory courses, like courses in computer programming. And what he was finding is that, he felt like he should be teaching these courses that had structured programming as an idea in them, but he himself didn't really know how to do structured programming. Because when his brain is going to go and try to figure out how to do one of these things, it's still thinking of the old school way of doing things. And so if he wants to say, like, okay, let's say we want to write this algorithm with no go-to statements, just using like a while loop or something like that, his brain is not wired yet to go that route. He's thinking of this other kind of machine in his head that's more based on the old way of programming. And so what he describes is sort of learning this process himself. And actually, later, when he goes to write tech, he talks about some of this, and he actually says that Dijkstra, Hoare, and Dahl, right, he credits them directly, in addition to other people, for like helping him and providing him the materials that he needed to learn how to do the structured programming, which he then would use actively to write, a program that's, fairly legendary. Tech is still used all the time today to like lay out papers, right? So in addition to that, Robert Floyd is also someone who helps him a lot as well. He describes basically going to Robert Floyd's office when he would have these situations where he's like, I want to teach this thing about not using go-to statements here, but I can't figure out how to do this thing without go-to statements. Like, what am I supposed to do? And the two of them would like work it out together. Or, in Knuth's telling, Robert Floyd would just tell him how to do it, because I guess Robert Floyd was better at it. Maybe that might just be Knuth being humble. I would not imagine that he couldn't figure it out himself, but it was probably nice to have someone else to work it out with. And while they were doing that, they happened to generate a paper out of it that was published in 1971. It was probably, worked on quite a bit before that, but it was published in 1971, which was actually about the idea of eliminating go-to statements from code, about not using them. And the reason that they wrote this paper is because lots of people had been talking about systematically removing go-to from code, meaning looking at code that already existed and say, here's how we remove the go-tos from it. Here's an alternate structure for this kind of code. And Knuth and Floyd found that, we can kind of prove there are some structures that you can't really remove the go-tos from. And they demonstrated two of them in this paper. So not only were they kind of into the structured programming thing, but they were also actively making contributions to sort of the emerging analysis of like, what sort of program structures will we support, why and how, right? So here's where we get to the point where we ended the first half of the talk. Ole Johan Dahl gives that book, Structured Programming, to Donald Knuth. It's not a watershed moment because Knuth has never heard of structured programming. It's a watershed moment because this is where Donald Knuth decides he's kind of entering the fray of defining what structured programming is even going to mean. And to that end, what he does is he publishes this sort of open review. He calls it Review of Structured Programming, and it's 3 informal open letters to each of the authors of structured programming, who are all, essentially friends of his, or at least, distant colleagues, you might say. So he's going to do one to each person. And he writes the first one to Edsger Dijkstra, and he basically says, look, this is a great book. You've done a fantastic job. I absolutely love it. But, of course, I don't agree with 100% of everything. And then he goes on to list all the things that he doesn't like about it. And then later on, as the year wraps to 1973, he writes one to Tony Hoare, and he says, this book is great. I absolutely loved it. I love everything about it. You've done a fantastic job. But there are several points worth debating a little. And he goes on to debate a bunch of points that are in the book. So kind of predictable. When he gets to Ole Johan Dahl's section, he's just kind of like, I loved it, but I don't know that I have that much to say. He doesn't really have a lot of objections. And I'm sure I'm projecting here, but I feel like that's just because, I like to imagine Donald Knuth has as much trouble understanding why we might want to do object-oriented programming as I do. But I do like that he calls Ole Johan Dahl OJ. And I like to imagine that that was just a common thing that he was called, because I'm imagining that if you would address a letter that way, an open letter that way, that must have been just what he was commonly called. So I thought that was kind of cute as well. So anyway, that brings us up to the point where we get the article that has premature optimization is the root of all evil contained in it, and not just the phrase contained in it, but actually an example and a worked example of kind of what Knuth might mean by it. And so what I'd like to do now is basically walk you through the important parts of this paper, because I know that if I say, hey, so everyone just go read this paper and you'll get it, don't worry about it, you've got all the background now, go for it, I know that no one's going to. So I'm going to walk you through the important parts, and fortunately for us, because it is a 41-page paper, there's very little that you actually need to understand to sort of get the gist of the target quote here. So first, I'm just going to point out the opening section here. This is how you know that the book Structured Programming is like forefront in Knuth's mind when he's making this article. And you can see here he talks about a revolution taking place and that reading the book Structured Programming will change your life, right? So he wasn't just being nice to his friends when he wrote those letters and, had a bunch of complaints, of course, but said that it was a great book. He really means it, and he says it as much in his publication that's right on this subject. Now, the rest of the paper pretty much, except maybe, the one part that we're going to talk about, is really just about the question if high-level languages should have go-to statements in them. And I'm just going to mention this briefly. It literally doesn't matter for us understanding that premature optimization is the root of all evil quote, but I just wanted to point this out because it's a 41-page paper, and almost all of it is about something else. And that something else that it's about is this question. So really, all he was trying to do with the paper was be part of this conversation that was happening where people were sort of asking, what do we actually need go-to statements for, or do we need them at all, when we move up from languages that are supposed to be really low level, like assembly language? Like if we're going to define sort of the successor languages to what we have now, do we need to have this, or will some other set of prefab template versions, right, like while loops and for loops and things like this, if then else, when we have those structures in place, if we got them just right, would it mean that you would never need a go-to at all? And a lot of people believed that the answer to that was just going to be yes, meaning we're never going to use go-to statements, it'll be fine. And I think that idea has merit. I mean, I'll be honest, I really don't program with go-tos. Even when I'm using a modern high-level language today, it's just not something that I do. But obviously, if you remember the Twitter drama from the first half of this talk, you know that people are still having an argument like, if it should be in the Linux kernel, right? Like, is that weird that they're using it? And things like that. So there were other people who believed, no, go-to probably does have a place. And what Donald Knuth was sort of wrestling with in this paper is, what are sort of all of the aspects that we might need to consider? What do we need to think about when we ask the question, does a high-level language need goto or not? And of course, we mean literal goto because everyone implicitly understands that there's gotos that kind of get generated, right? Like the processor is going to be doing jumps, so that's not the question. It's just what will the constructs look like when you're actually programming them? And Donald Knuth, in his conclusion, actually just says as much. He just basically says, I think the big question is whether or not like the ultimate language that we end up getting. And believe it or not, I had to cut this part for time, but it's kind of fascinating. If you're into papers, please read it, because this section is kind of amazing. He's talking about, contemplating like by 1984, I think was the date, I may be misremembering it, but by 1984, maybe we would have kind of like the final language that we'd ever need. So, Bill, sorry, like in 1984, they were going to have the only language they would ever need. So really, he was just trying to say, like, in this hypothetical future where we're using these amazing programming languages that we're going to build, will they have goto, or will goto just be something that's kind of used as a low-level primitive that is maybe part of, inline assembler or something like that that's happening, but not really a construct that's used most of the time? So how do we get from that to this quote? Because they're not really very related, right? It's hard to understand how you end up with this in a paper that's just about should we have goto statements in higher level languages. It doesn't make a lot of sense when you think about it. Well, if you want to understand where it comes from, you really only need to understand these 3 pages. Obviously, it helps to read the whole thing because there's stuff for context everywhere in the paper, but mostly all you need is those 3 pages. And the section on efficiency, remember that I said this is where premature optimization is the root of all evil comes from. The section of efficiency is like right there, and the only reason you need to extend it back a little bit is because there's sort of a motivating example that starts a little bit before it that's carried through into the efficiency section. So these are the 3 pages, and I will walk you through the important parts. That is where premature optimization of the root of all evil occurs. So that's where we're headed. That is the first example we need to know over there on the left. So the example that we're working with is really very simple. You have an array. It is 1-based because that was a common thing in ALGOL. So you'll note that it doesn't start at A0, it starts at A1 and goes to AM. And the idea is this array just has values in it, whatever they are. And we're going to have a value called X that we want to search for. We're going to go through the array, and if we find it, what we want to do is say, okay, I found it. If we didn't find it, we want to append it to the end. So it's basically linear search through an array with append at the end of it. And as a bonus, we want another array that we're going to keep at the same time, which will just tell us how many times we found any particular element of the array. So at first, you would have zeros. There's nothing in the array at first. When you add something, that's going to be 1 because it's been found 1 time. If it gets found again, it goes up to 2, 3, 4, and so on. So it's basically a frequency count of times that people have returned that value. So just 2 arrays with an append. Very, very simple. Something everyone would be comfortable writing today, certainly. It's no complex algorithms, no nothing. And this is the example code that he gives in what he calls sort of pseudo-ALGOL. It's exactly what you would expect. Go through, well, I guess I should say, it's exactly what you expect if you're trying to demonstrate how you would write this with goto, right? You go from 1 until the array, so you just step through all of the elements. If one of the elements is equal to what you want, then you jump down to the found clause where you increment its frequency. If, on the other hand, you fall out of the loop because you haven't found it, then you go ahead and expand the loop by 1 element and place the new element in it, initializing its return count to 0. Now, it may be a little bit weird that return count is to 0, but remember, it will still execute the found clause, so it will bump it up to 1 after that. Now, he shows example 1, and then he goes on sort of a bit of a weaving case about what you would need to do if you wanted to have this exact code run, but you didn't want to have gotos in it. So you wanted to do the same operations in the same order, but without actually using the gotos. And we don't have to worry about any of that because it doesn't have anything to do with premature optimization of the root of all evil, but that's what he's going to do in there. And that's very common for this entire article. Like, that's what most of the rest of the article is like, let's look at this simple snippet of code that has some gotos or doesn't have some gotos, and let's talk about removing or adding the gotos and what does it mean when we look at the actual results. So we can jump forward to when he starts talking about example 2, because that's where we start leading into the efficiency section. And what he says is that, look, example 1, and because of a bunch of things that we've skipped over, he's just saying, like, look, you could do these transforms, but they wouldn't necessarily come out to be the same. So example 1 has often been used to defend the goto statement, but he says that doesn't really hold much water. And the reason for that is you really shouldn't be searching for things that way anyway. And not because you're using a goto, that's not the problem. The problem is this set of operations is not the right set of operations to be doing anyway. What you should have done is you should have started by just appending the thing right away. So just add the thing you're looking for at the end right off the bat. Don't even check. Then you can just loop through without really counting, without looking to see if your counter has expired. You can just look to see if you found the element, because you always know you will eventually find it. You just might find it when you get all the way to the end and found the one that you stuck on there yourself, right? So that just makes the loop a lot simpler, and it doesn't have to do as much work in the body of the loop, which of course is the important part if you're trying to make this code run reasonably. Then at the end, you just check, did I have to go to that final element to find it? If I did, then expand the array by 1. If I didn't, then I can just go ahead and increase the frequency count of the one I found because I have found it inside the array. So really, again, incredibly simple transformation he's talking about here. Just append right off the bat, and then just see whether or not when you find it, if you found the one you appended, and that lets you know whether to grow the array or not. Really simple, right? And so he talks about this in terms of its performance. He's like, example 2 beats example 1 because the inner loop is faster. And then he gives sort of an example here now for the first time in the paper of like figuring out how fast this might run. And he does it in a kind of way that's a little unusual, but you can understand because it comes, Donald Knuth did a bunch of algorithm analysis as well. So you can kind of understand the way he breaks it down. He says example 1 will make 6n plus 10 versus example 2, which will make 4n plus 14 accesses to memory. So he's just measuring accesses to memory. And again, that's a little bit strange. We'll talk about that later, but that's what he's measuring at that time. And so he says, if you compare those two, you're saving 33% of the runtime, right? Because I had 6n, so if I'm talking about the body of the loop, which should dominate the runtime because it's the thing that's going to be running the most as n grows, then if I had 6 and I saved 2 to get down to 4, well, that's, a third. So we save a third of the runtime by making this transformation. Therefore, we don't actually need to worry about the fact that we couldn't use the first algorithm by removing the gotos from it. So now we get into the section on efficiency, which is the section that actually has the part that we're aiming towards. And he kind of starts to pontificate here. He kind of starts to expound on some things. So he kind of moves away from talking about anything concrete. And he says that experience has shown that most of the running time in non-IO bound programs is concentrated in 3% of the source text. That's his assertion. And he says that there's usually a short inner loop whose speed governs the entire program. So if you sped it up by 10%, the whole program would speed up by 10%. This is Knuth's assertion in the opening of this section. So that's how he thinks about how programs work in terms of their performance. And he says, I now look with an extremely jaundiced eye at every operation in a critical inner loop seeking to modify the program and data structure. So everything's on the table so that some of the operations can be eliminated. So if he knows where the critical loop is, he's like, I'll do anything to make that thing go faster. And he says that the reasons that he likes to do that is it doesn't take very long. The payoff is real, like he does see the programs run faster, and he can then afford to be less efficient in the other parts of the program because he knows that he's made the whole thing faster by optimizing that critical loop. Okay, so that's what he says in that section about efficiency. The next section about efficiency has another example in it, and that is example 2a. He says, if example 2 were really critical, so that thing we just saw where you append and you search, and then you just use whether or not you found it in the array to increment the frequency or append. He says, if it was really, really critical, I would double it up. He calls it doubling it up. And he shows this new example where the gotos come back in. And so again, although we're focusing on the premature optimization part of this, it's worth remembering he is trying to talk about gotos. That's what the paper's supposed to be about. So the gotos come back in when he wants to do this doubling up, as he calls it. Now, what is going on here? Well, example 2 I've put at the top, 2a I have put just below it, and you can see that the initialization code, so 2 is the one we already did. We already looked at that one, right? The initialization code is the same. The end of it, when you find something, that's the same. So the only difference is here. The while loop has been expanded. And how has it been expanded? Well, really very simple, actually. He's going to check for one element, and if he found it, then he knows, well, I'm done. If he didn't find it, he also checks the next element, right? So he checks 2 elements at a time. And then he knows whether he needs to repeat the loop by advancing 2 and starting to look at the next 2 elements, or if he can just increment by 1 and let the loop finish as it is, right? So he hand unrolls the loop. This is basically hand unrolling of a loop, taking it from doing 1 element per iteration to doing 2 elements per iteration. And he just called it doubling up, but we would today call it unrolling. He then does the same kind of runtime analysis, the exact same kind as he did when comparing 1 and 2, he does for 2 and 2a. And he says now it's reduced to 3.5n because, again, he doubled it up, so it's hard to say exactly how many because it depends, right, what's going on. So he says the runtime has been reduced to about 3.5n, and remember before he said that the second program was 4n, and so now you've saved about 12% over that previously better version. And he inserts a parenthetical here, which I'm including because, again, I want to give you the full scope of like what is being talked about when we talk about this phrase. He does say, of course, if we want to improve on example 2a still more, especially for large M, we'll use a more sophisticated search technique. But let's ignore that issue at the moment since I want to illustrate loop optimization in general, not searching in particular. So in his head is the idea that, okay, we might also make some pretty drastic changes to this program. We're not just considering things like hand unrolling the loop. We're considering things like maybe let's switch to a binary tree or who knows what, So we're almost there. We then get to a section that I guess I'm going to describe this next part as a little bit of a roller coaster. He's kind of like goes one way, then goes the other way, and he's really, I would say, trying to talk about both sides of this issue. He's pretty even-handed, I guess I would say. He says the improvement in speed from example 2 to 2a is only 12%, and many people would pronounce that insignificant. And he says the conventional wisdom is that efficiencies in the small like that, like 12%, they're just not that important, right? We don't need to worry too much about that. But he says that he thinks that that's an overreaction. He thinks that's just because optimization like this has gotten a bad name because people have maybe been doing too much optimization or optimization at the wrong time or optimization of the wrong parts of the program. And so they're creating things that are more messy and harder to deal with because, they've optimized something which maybe didn't need to be optimized or shouldn't have been optimized yet. So you can kind of see where this is going, right? But he then asserts, well, okay, maybe that's true, but if this were an established engineering discipline and you could say I was going to get 12% improvement and it wasn't that hard to actually do, I just have to concentrate on this critical loop and I make some modifications to it and I can actually get a 12% improvement, that would not be considered marginal, right? Like if you were going to say like this jet engine is now 12% more efficient, they wouldn't be like, I mean, the jets are fine the way they are, man. It's cool. So, he's trying to point out that if we want this to be a real thing, if we want computer science to be a science and engineering of, software to be software engineering, not just screwing around, then we have to take things like this seriously because that would be what you would be doing in another context. So now we get to the end. This is where it actually happens. So in this section of the paper where he's going to finally say the catchphrase, he says, programmers waste an enormous amount of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency have a strong negative impact when debugging and maintenance are considered. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. There it is. And he says, yet we should not pass up our opportunities in that critical 3%. A good programmer will not be lulled into complacency by such reasoning. He will be wise to look carefully at the critical code, but only after that code has been identified. Now, that part is often quoted by people who are trying to be more pro-optimization, let's say. And this next part here, which I'm going to include because I think it goes with the whole quote, that's just right after it, strangely, I don't often see quoted. But it's actually one of Knuth's most strongly held beliefs. And so I want to go ahead and read it in its entirety. He says, it's often a mistake to make a priori judgments about what parts of the program are really critical, since the universal experience of programmers who have been using measurement tools has been that their intuitive guesses failed, meaning like you can't guess what the critical loop is, maybe unless you're really experienced, unless you're actually measuring it. And so he says, I've become convinced that all compilers Not some, not compilers for low-level languages, but all compilers written from now on should be designed to provide programmers with feedback indicating what parts of their programs are costing the most, meaning like, when I do this compilation, it will tell me, here is where the critical parts probably are. And he's like, unless you turn that off, you get that every time. He's like, it's in there by default. All programmers, all compilers, he says. This is not conditional on anything. So we're talking about Susie Meyer, right? When she comes and programs PL1, she has to receive that log, right? She has to receive a profile of her program in addition to the PL1 compilation. Everybody, every last person. And I know that's one of his most strongly held beliefs because he actually says it in 3 different papers. There's one from 1971, one from 1973, and one from 1974. And he says exactly that thing. It's not in exactly the same words, but it's all like every compiler has to do this every time. So this was supposed to be a paper about GoTo, but somehow we've gotten to the point where Donald Knuth is making recommendations for all compilers for all time about something that really doesn't have anything to do with GoTo. So he's kind of gotten off the rails here, and that's like the first thing that you might notice about the premature optimization is the root of all evil section, is that it's on its own orbit. Like, something set him off when he was writing that section, and he was just going to go. Like, he wants to talk about his whole idea about efficiency, not just as it narrowly pertains to something about a change that has to do with GoTos. Okay, so I just want to ask a few questions about it, because to give you some perspective on what I was thinking when I read this for the first time. And the main thing was this. I was like, he kind of went off on efficiency here, and it seems like he cares a lot about it and he wants to talk about it, but there's no timings for anything. If you look through this entire paper, he never talks about like, so we ran these things and we timed them and we saw that like this loop was faster than that loop. And to me, that's kind of important even for just the main thesis where he's talking about like, is this loop with GoTos better than this loop that doesn't have GoTos? You know, I would expect to see like some actual runs. We fired up the IBM 360 and we ran it and we saw that this one was indeed faster, not just it has less operations as I count them on the page, right? And if you look through, the only thing I was able to find, and maybe you'll be better than me at finding it in this paper, the only thing I could find was one little passage where he's talking, I think example 8, it was in the quick sort section, I could be misremembering, but he's talking about example 8 and he says, empirical tests have borne out my prediction that is in fact about 15% slower than the book algorithm. There's no citation, he just says that empirical tests have shown that, and he's talking about an actual test. So that maybe is a timing thing, I'm not sure. It doesn't have any real information about it, and I wasn't able to find any corroboration, so that's the only thing I found. Everything else is sort of about abstract efficiency, more like big O notation kinds of feels, even though they're about computers' more specific performance. And he goes through it pretty concretely. Like, he explains what he is counting and how. It just doesn't seem to necessarily be tied to any actual machine timings. And this might be just because he was trying to make it more broad audience, like he didn't want to be like, this is just for the IBM 360 or something like that. But he doesn't really give a rationale. He just says, in order to make quantitative estimates of efficiency, I've counted memory references for data and instructions, assuming a multi-register computer without cache memory. So what he's basically saying is like, we're just going to boil this down to like, things are efficient or not, or the degree to which they're efficient is based on how many times they will probably have to access memory. And we're going to assume that there's no caching. Now, he talks about how the costing goes. He says, we're going to assume that an instruction costs 1, because I had to go fetch the instruction. And we're going to assume that any reference to memory costs 1. But we're also going to assume that like small constants and things like that would have been baked into the instruction. So like if I'm going to add 1 to something, I'm not going to assume that I needed a round trip to memory to fetch the 1. I'm going to assume that was part of the fetch for the instruction. That's his estimation. And you can see he even has tables where he shows it. The instruction, this is how he's like sort of notating. It's not a specific assembly instruction, just like whatever assembly instruction your machine would have to do to like load 1 into the first register. That's the example of a kind of instruction. How many times it was going to get executed. So this is in init code, so it's only going to happen once. Things inside the body of a loop would happen n times, or n minus a for cases where it's like found or not found, et cetera, et cetera. And then the cost, which is that estimate we just talked about. How many trips to memory it's going to take. So that first one, right, R1 is going to get initialized to 1. That's a register. We're putting 1 in a register. It only costs 1 because this instruction doesn't touch memory other than to load the instruction, right? That's a small number, 1. It can be baked in the instruction, so we have 1 access to memory to get the instruction, and then we're good. But something like initializing register 2 to the count of the array, M, that costs 2 because we had to fetch the instruction, and then we have to fetch the value of M from memory. So that's how the costing's going. And again, in my head, I'm thinking, this is kind of weird as I'm like working through these tables and looking at how he's doing this costing. And the reason it seems kind of weird to me is the kind of things he's analyzing are really kind of hairy, right? And I mean, they're supposed to be hairy because the whole point of structured programming was like, let's try to have less bugs by removing things like go-to statements that create kind of all these weird control flows that are hard to reason about. And so by necessity in the paper, he's talking about pretty crazy stuff with lots of jumps in it, jumps to different places, different kinds of jumps that are going on all next to each other. And if you think about this from the perspective of hardware design, this creates a lot of issues for things like, I want to track branch targets, or I want to do branch prediction and things like that. Now, you may think, well, Casey, that never existed back then. That's only a modern thing. Not true. I went back and kind of looked at what sorts of computers they would have at Stanford. I know they were on IBM 360s. I don't know if they specifically had a Model 91 yet, but they eventually did, so I can't tell exactly where they would have had it. But as early as 1967, you would have already been reading about this model. And of course, this paper isn't until 1974, right? And if you look at the kinds of things that they were doing in the Model 91 360, it just sounds like today. You read it, it just sounds like a modern CPU. It says a separation of 8 double words or less defines a short loop. So if the instructions for a loop fit in 8 double words, this number being chosen as a hardware performance compromise. If this test is satisfied, the instruction unit enters what is termed loop mode. First, the complete loop is fetched into the instruction buffer array. In other words, a loop cache, which they had in 1967, although I don't know if the first machine was actually then, but they had already designed it in 1967, after which instruction fetching ceases. Consequently, the address port to storage is totally available for operand fetching, and a 1 instruction per cycle issue rate is possible. Meaning that even at this time, in the late 1960s, you would have wanted to know how big your loop was. Because if it fit in 8 double words, you would run out of a loop cache. You'd run right in that cache, and you wouldn't have to fetch the instructions anymore. So that kind of costing, where it's like it's going to cost 1 to fetch the instruction and then to fetch the memory, is actually not correct if you're on a machine even in that era. Now, earlier 360s and earlier machines that Knuth was probably programming on, that would not necessarily have been true. So I don't know whether his mindset was, we're not going to worry about this sort of thing yet, or if he simply wasn't paying attention to this space yet because maybe that wasn't his focus, or if it was just like, look, I can't write in this go-to article about loop caches, dude. Like, I'm trying to make this broadly applicable to people who are on all sorts of hardware, so we're just going to keep it with something that most people would understand and not the cutting edge of CPU technology at the time, even though we at Stanford might get one of these, other people aren't going to have it. So I'm not sure, but it's just worth noting that these CPUs were already pretty crazy. In fact, here's a graph from that article which talks about like how branches affect the instruction issue rate and things like this. So the stuff that we think about today is actually nothing new. It goes back like 50 years or more, 60 years at this point almost, and they were already doing all this sorts of stuff. So that's one thing that was a little bit odd when reading the paper, and I kind of wanted to know more about it. But the bigger thing for me when I read through those sections is like, I didn't understand the 97.3 thing, right? There's this strong sort of 97.3 energy that's happening. He's like, we should forget about small efficiencies, say about 97% of the time, premature opposition to the root of all evil. And he's like, but we should not pass on 3%. So it's like 97.3, these numbers are kind of, I mean, if you were just making something up, you'd say 80-20 or something, right? Or 90-10. Like, this is fairly specific. He's not just, imagining some hypothetical thing. He clearly has something in mind. And I realized as I read the paper more carefully and really tried to work through it and like read it for real, not just like skim it, I realized, oh, right. he already said, and I showed you in the earlier part, experience has shown that most of the running time in non-IO bound programs is concentrated in about 3% of the source text. So this is actually a number he has in his head, this 3%. It's not a number he pulls out just for that comment. That's what's usually quoted when more of the quote is quoted. It's actually coming from a thing he earlier talked about, which is this belief that 3% is a magic number. So this was like, where is this 3% coming from? Experience has shown, well, what's the experience, right? And you have to connect those two so I can understand why a lot of people maybe miss it, because the 3% is originally said on the left side and then the quote doesn't come till like the right. But still, to me, this is pretty critical. In my head, I'm like, I want to know more about this. And following up on that, if you remember right after that original, experience has shown 3% part, is this part where he says, speeding up the inner loop by 10% speeds up everything by almost 10%. And when I read that, even the first time I read it, I was like, what kind of critical loops do these guys have? I don't think I've ever sped up a critical loop by 10% and the whole program ran faster by 10%. Maybe if I was really lucky, the whole program ran faster by 5% or something like that. But it's pretty rare unless this program now did basically nothing for that to be true, right? And so I was like, well, maybe in those days, the program was just like one loop and there was nothing else in the program. So 10% and that was it. You speed it up by almost 10%. So I really kind of wanted to know more about that as well. Like, how did he get that? And I started imagining in my head, I'm like, so what is almost 10%? You speed up the critical loop by 10%, the whole thing gets faster by almost 10%. What does that mean? Does he mean 9.9%? Is that almost 10? 9.5%, that would round up to 10. 9%, it's almost 10%. And I kind of said, I think, hopefully you'll agree with me that it's fair to say 9% is probably like a floor. If you were going to be 7%, you wouldn't call that almost 10. You're only speeding the thing up by 10% to begin with. So if you're like, I sped it up by 10%, and good news, I got almost 10% speed up. How much did you get? 7%. You'd be like, what? You're off by quite a bit there in terms of a ratio, right? So I wanted to know, if I just took those statements that he made and I did the math, I wanted to know, okay, what percentage of the total time would have to be spent in this hypothetical critical loop that he's talking about in order for these things to be true, in order for a 10% speed improvement to result in at least 9% of an improvement to the whole program? Because it's math, which I suck at, by the way, and Donald Knuth is awesome at, so that puts me at a disadvantage, but I wanted to know, what would be the total time? And so I just did, thankfully it's math I can do. You don't require Donald Knuth for this, thankfully. It's math I can do. I just wrote it out and I was like, okay, let's suppose we have the total time, both unoptimized and optimized, and the critical loop time C for unoptimized and optimized. And I was like, I can just write it out. I can be like, the difference over the total, right, is going to be 9%, and the difference of the critical loop over the unoptimized critical loop, that's going to be 10%. And then I can use the fact that I can relate the total time unoptimized and optimized by just using the loop timing. That would give me 3 equations in 4 unknowns. So that allows me to solve for the unoptimized critical loop time in terms of the total unoptimized time, right? And since this is not a math talk, I'm not going to try to explain that anymore. Almost everyone in the audience will be better at math than me. So I'm imagining you will look at that immediately and just go okay, yes. And I did actually go ahead and check this with Dimitri Spanos because I was like, if I'm going to put math on a slide, I want to make sure that it's at least in the ballpark of being correct. And I don't mean to put Dimitri in harm's way here. So if there is a mistake, it's definitely my mistake. But he was like, yeah, that's totally fine. That's what that would do, right? So I just went through these and I did them. And I got 90% pretty much no matter what I did. So even if I pretended swapped the variables around and said, oh, well, maybe it's stated as a percentage of the optimized time that comes out of it as opposed to the original starting time, I tried them all ways, and it ends up being approximately 9. It'd be 91% or 90 point something percent. So that means that if you take this statement, the 10% one, in conjunction with the 3% of the source text, it means that Donald Knuth is stating in this section very specifically that 3% of the source text must account for about 90% of the runtime. That's just what he said. And I don't know any other way to figure it. That's the best I could do. And if obviously after the talk, if anyone can figure out another way to interpret this, I'm all ears, but that was what that sort of said. So I'm like, all right, well, that doesn't really make any sense. That sounds wildly optimistic, so I'm gonna go dumpster diving again. I wanna know what's going on here. And thankfully, there are 2 references that are listed when he's talking about that experience has shown that most of the running time in non-IO bound programs is concentrated in about 3% of the source text. So there are 2 things, 2 breadcrumbs we could follow to try and figure out where he got this idea and whether it's actually from real data or whether it was maybe he was kind of talking off the cuff and didn't really remember, or maybe it wasn't really as rigorous as he was. He didn't mean to sound as rigorous as I'm taking him for. I don't know. But we do have 2 references we can go through. The first one is this thing called the Execution Time Profile as a Programming Tool by Dan Ingalls. And Dan Ingalls is actually another person who got shortchanged in the big oops because we didn't really go very much into Smalltalk last year when I gave that talk. But Dan Ingalls is actually the person who first implemented Smalltalk. Much like Lisp was sort of created by John McCarthy but wasn't initially programmed by him, the very first version, the very first experiment with it. The same was true of Smalltalk. Dan Ingalls was the first person to go like, I'm gonna actually try to get this language running. And so he would have been in that lecture if we had had more about Smalltalk in it. And this is a paper that he had in a thing called Compiler Optimization. It was like a symposium, and it was a collection of papers that were kind of parts of presentations at the symposium. And this, I don't know if anyone else can find it. I can't find it. Like, I have looked really, really hard for a digital version of this paper anywhere, including like, I buy papers all the time for preparing like this kind of talk, and I couldn't even find like a paywall version of this. It was kind of like never digitized, I guess, or if it was digitized, I couldn't find it. So anyone out there with better search skills than me, maybe you could find the digital version of it, but I certainly couldn't. So the only thing we can look at digitally is this Donald Knuth paper, so he's referencing himself, called An Empirical Study of Fortran Programs. That's the only one that we can actually get as like a PDF, right? And so what is this paper, An Empirical Study of Fortran Programs? Well, this is a report of a 3-month study that Donald Knuth did with students in the summer of 1970. So shortly after he arrived, remember he arrives at Stanford in 1969, and this happens in 1970. So this is like right away, basically. This is one of the first things that they're doing fairly shortly after Knuth and Robert Floyd arrive. And what they did is they examined a large number of Fortran programs to see how frequently certain constructions were used in practice. Over 250,000 cards. So again, this is all happening on punch cards, right? Representing 440 programs were analyzed. And they had to get them from somewhere. So the first thing they tried was, I've been using the term dumpster diving. Well, they went dumpster diving. They were like, I'm gonna go through the wastebaskets. Like, we're gonna go in the computer center, we're gonna go into the bins, we're gonna take out the listings or the punch cards or whatever anyone's thrown away, and we're just gonna go use those as the programs. That's idea number 1, that's how we're gonna do it. Because they can't go to GitHub, right? It doesn't exist. That didn't work because they were like, oh, right, if people throw away the program, it was probably because it didn't work. So it's like, we probably could do something with this, like if we were doing something that was less about studying the things that we want to study in working programs and more about like what kinds of bugs people have, this is probably a pretty good idea, like man the wastebaskets. But for what we wanted, not gonna work. So then they were like, all right, I got a better idea. We're gonna stand next to the computer. We're just gonna have someone standing next to the computer. And whenever someone comes in with their stack of cards that they're ready to run, we're just gonna be like, hey, listen, we're doing this study and we kind of wanted to collect programs, and like, don't take this the wrong way, but like, is this like a program that works or is this like really buggy? Like, and how good of a programmer are you? Like, do you really know what you're doing, or are you just kind of screwing around, right? And they were like, okay, this didn't work because it was very time consuming. They had to explain the whole thing to people who were like, what are you talking about? And it was like, they had to ask these embarrassing questions about like, what is the state of your punch card deck? So it's like, okay, maybe that's not the greatest idea either. So then what they did is they just straight up just invaded everyone's privacy. They were like, all right, as long as they're like, it uses the term semi-protected. So I don't even, like, not unprotected. He says semi-protected files stored on disks looking for a source test. He's like, we're just going to go through like the magnetic storage, I guess, looking for things that people have committed to that, and we're just going to straight up take them. Like, no asking, all your programs belong to us, right? So they collect 20,000 cards for Stanford. They also work with Lockheed Martin, not Lockheed Martin yet, sorry, got the wrong time period. Lockheed Missiles and Space Corporation. They also work with them to get some programs from industry. So they get another 440 programs from Lockheed Martin. And they build this table, they do a bunch of static analysis, and they're just looking, because again, remember, I realized when I put these things together, like now everything I'm just like, oh, of course everyone knows. It's like, no. They wouldn't, like you've mentioned this briefly in one slide. So remember, they are, part of their department, charter is programming language stuff. Like we want to learn about what we need to compile, what we need to optimize, what we might want to do for language design. Like that's part of what they're doing. So they're going through and they're like counting the statements. Like how many assignments do you do? How many go-tos do you do? How many of these different types of things do you do? And when you look at this table, you're like, okay, like these are pretty sizable programs that they looked at. 78,435 assignments. I mean, it's tiny compared to today, but that's like a fairly complex piece of code. Until you realize this is the total. That's the total number of assignments in all the programs that they had. A typical program was 178 assignments. 63.5 ifs, 56 go-tos, and so on. So these programs are super, super tiny, right? So this idea that Knuth is getting about how programs break down, it's important, and like how their critical loops may be in the source text, whatever. It's important to now start to keep in mind the sample that he was looking at and that he's referencing here, and that he personally, that kind of affected him and was like, oh, I saw this, and so I'm now thinking 3% and this sort of thing. That's coming from very small programs, so much smaller than anything we would think about today, right? I mean, I don't think someone could probably start up a JavaScript program without doing way more assignments that are in all of the programs, probably times an order of magnitude, right? So these are very, very tiny programs by today's standards. The only people who probably would know anything about this sort of size program intuitively would be like 4K demo scene coders or something, right? And Donald Knuth in this paper does say this. In the 1974 paper where he's talking about premature optimization as the root of all evil, he kind of states it more definitively. He's like, experience has shown it's 3%. But in this one, he's like, well, who knows? Like, we just did our stuff. We just did Fortran. We don't know how accurate it is, right? So he kind of says, like, I'm not really sure. And he says, we hope other people will, like, do these things and publish those so that we could see. But I guess no one does, or if they do, I shouldn't say no one does, because I'm sure people were doing it, but what I mean to say is, I guess no one did it in a thing that Knuth saw, or if he did, he didn't think to include it as a reference to like support the claim of the 3%. So in this paper, he's kind of more open to the idea that this might not be representative and 3% might not be a number for everybody, right? So in terms of the actual thing that we wanted to know, though, how does the 10% speed up and the 3% thing, right? The 3% accounts for 90%, that part. Is there anything in the paper that really tells us where that comes from? And the answer is, well, not really. There's just this thing that says, we also found, again with really no information, that less than 4% of a program generally accounts for more than half of its running time. Now, technically, that does include 3% takes 90%. Because 3% is less than 4%, and 90% is more than half. But in terms of an actual reference to something I can use to corroborate, this is not really helping me, right? Because that includes a whole range of statements we could make, and we certainly wouldn't definitively make them. Now, I do want to mention, at this point, that the paper does include sort of how they did the measurements. And I was kind of worried about this talk being infinitely long, so I didn't include a section on that. I had a bunch of things, and there's some interesting things in it, but I was like, we probably need to cover this. But I do want to mention it briefly. They did have two ways of checking how you were going to spend time on a computer program. Weirdly, nowhere have I seen mentioned in any of the Knuth publications just timing the program. Like the idea that we would like stopwatch time how long the program took. And nowhere did I see any indication that they had a way to do something like sample a cycle counter or some kind of clock internal to the machine at 2 points in the program and diff them. So the kind of thing that we would currently do for timing like a critical loop, there's no evidence that they had a way to do that. Not that they couldn't do that, just that they hadn't made one. So, I'm not trying to say that the IBM 360 couldn't do this because I'm not an IBM 360 person, but they certainly didn't have one, or if they did, they never mentioned it. So the two things that they had, one is a sampling-based profiler. So the IBM 360 and lots of computers at that time, I guess, did have a way to wake up every so often, just like a modern-day sampling profiler, wake up every so often and take a look at what the instruction pointer was, like basically where it was currently executing. And so you could make a histogram of like, if we did this every so often, where in your code were you? So that would be one fairly reliable way to know where time was being spent. Now, you couldn't necessarily know how much time was being spent because this is a sampling-based profiler, and sampling-based profilers require extra information to really give you a timing from that, but it does let you know the distribution in a fairly realistic way because the hardware is doing the sampling, so you know that it's like, it's something reasonably fair in that case. The other thing that they had was just instrumentation, where they would go in and they would take the program, usually by means of an automatic translator, and they would have the program get marked up with sections where every time you were in a section, they would increment a counter. So it'd be like a code coverage tool, right? So you could know the frequency with which you were hitting each individual instruction, just in terms of how many times it was run. This doesn't really tell you anything about how long it takes to run. You can only sort of guess what that might be by looking at the resulting code and going, here's how long I think that might take. But it does, again, tell you something at least about how often things were run, not necessarily how long they took. So unfortunately, that kind of leaves us with this reference we can't look at, right? The only place that we might be able to find a justification for this 3% takes 90% thing, which is kind of important to the whole thing because it's like, this is the basis which he starts talking about and how he ends up getting to premature optimization as the root of all evil. It's kind of important that this be corroborated to me anyway. It seems like a critical piece. But there's no actual way to get at this information digitally. It's not possible. So like the only way that you would be able to know, like if you actually wanted to know if this contains that information, short of, I guess, asking Dan Ingalls about it, or maybe Donald Knuth, is you would need to go to some kind of really good tech library that had fairly obscure old publications in it and maybe look there. Or you could do something like wait till someone was selling it on eBay and buy it, right, and look at what's in it. And that seemed like a good idea at the time. So I did. And the good news, the good news here, I probably should have had it open to the page, but the good news here is that it's in there. And in fact, here it's even got some diagrams. This is the article in particular, right? And this was really exciting for me when I found this because like, awesome. I can chase the whole thing down, right? It made me go from this where I was like, oh, I'm so frustrated, to this where I'm like, yes, we have hit pay dirt, people. So I scanned it in so you guys don't have to try and squint at this. I scanned this article, and here is the book. There in the table of contents is exactly what we're looking for. And in this, Dan Ingalls talks about basically this exact thing. He's like, hey, I was part of this thing we did at Stanford. We're in the summer. We went dumpster diving and got all this code, and we were trying to analyze it. And one of the things I did was sort of extend this Fortran analyzer thing to be able to give really convenient printouts that people could use. And what he does is he says, this is how it worked. We have the Fortran code that comes in here, and it will tell you things like how many times it was executed, and then how much time we think that that would probably account for. And for things like ifs, we'll tell you how many times it was true versus how many times some other if statement got, basically how many times did the body of that if get executed. And again, we can confirm the IBM 360-ness of it, although not which specific model, because it's right at the top of the printout as well. And so what this program did, which was called Fortune, by the way, it was originally called FORDAP, I think, and then it became FETE when he did a tech report, and then finally it was Fortune when he wanted to sell it. He was actually selling this program. it instruments that code. So this is the same code here. I don't know if you can tell because I kind of had to like cut and paste it, but it's the same Fortran code, and then it inserts these counters. Where you can see it just inserts these counters to try and count how many times you hit things. And for things like if statements, it will try to add little like pieces to count the if statements, whether or not you took them and things like that. Now, this gave a much more like, because now I know this is what they were using, right? This is what they based a lot of what they were thinking in the Donald Knuth paper where he's talking about all this stuff, right? So the paper that he references for the 3%, 97% thing and all of that stuff, this has a much more complete explanation of how the time costing is actually working. He basically just says, look, all we do is we scan the Fortran code. I just look at the Fortran code, the program scans it, and it basically just comes up with a cost estimate for various pieces of the Fortran code. And he even calls it like extremely crude. He's like, look, this is very crude. So he's not even, they're not even trying to make any pretense that this is a very accurate profile or anything. It doesn't even work on the assembled Fortran. Like it's not working on the machine code generated by the Fortran program. It's literally just like syntactically, the Fortran syntax code itself is basically what it's using to come up with this cost. So the costs are probably like, very inaccurate on any kind of a machine that might do something interesting, although maybe they could be pretty accurate on a machine that was like very lockstep and didn't have any particular type of superscalar or any sort of like, or the caching and those sorts of things. So the question is, can we find out the answer to the 3% accounts for 90%? Like, can we find an actual piece of data in here that supports this claim? And the answer is, we can actually find something that completely refutes it. So in this paper, it's very clear where the 3% comes from. It's right there, right? 3%. But the problem is it's 50% of the program's execution time that accounts for, not 90. So it is a significant part of it, but if you sped it up by 10%, you're not getting anywhere near 10% of your total time back. So I think this might have just been a case. You can even see here like the counts for fraction of 50% as it goes and how many programs there are. So that was the layout of the ones, they try to take a representative sample. So I think this is just a case of maybe like this was supposed to be more of a philosophical statement on Knuth's part, but the actual, if you read it, the way it's stated makes it sound much more forceful than the data actually is. The data is nowhere close to 90%. And you can see that if we look more closely at a complete breakdown. You can see that like the routine that accounts for the most percent in this program that has a complete dump listed as an example in this book, it's only 66.7%. And it looks actually not that dissimilar to if we had a hotspot program today. If you were to kind of fix whatever bad was happening in that 66.7, you would be left with a pretty nasty flat profile. There's lots of pieces that are taking time there. It's not a 90-10 at all. It's something much more like a 70 or 65-35 or something like that, right? So that's everything. That's the entirety of the read-through of the paper. At this point in the talk, since I've pretty much come to the end now, originally when I kind of like mapped this out in my head, like how am I going to make this into a talk, my thought was like at the end, because this is how talks typically go, there should be a part where I'm like, so this is how you should interpret premature optimization as the root of all evil, right? It's like, this is how I want to recast it or something like that. But I think, and all I can say is, to give you a little bit of perspective on what it feels like when you do something like this, when you go through a ton of history like this, and you do it in a short period of time, so you're spending a month or something, looking at all these things and reading, what ends up being like thousands of pages, and you're not like reading every single one, you're reading some of it very closely and others you're skimming. It's just a huge amount of information, and it starts to like soak into your brain in really exactly the way that I am glad that it does, because it's why I do it. I like to get this sort of gestalt sense of it from doing that, and that's the whole reason that you'd rather do it than to just, have somebody else tell you what was happening or something like that. And so when I started to think about how I was going to wrap up the talk, when I came to this part, I was just like, I couldn't do it. I was like, I don't want to do that. Like, I don't want to actually say what the interpretation of premature optimization as the root of all evil is. And the reason for that is because this whole thing, like the whole story, that whole first half, for example, and the whole thing that was going on at this time was all about like abstractions, right? It's all about like, let's try to abstract some things and work at a higher level so we're not dealing with all the details, right? And so my brain was kind of thinking about that a lot and thinking about that that's what they were doing. And I started to think about like, really, premature optimization is the root of all evil is like its own kind of abstraction, right? It's a thing where there is all this stuff going on and a tremendous amount of interesting things, and there's all these details that actually matter, and they matter especially if you're going to try to take anything away from this phrase. Like if you're actually going to try to take anything away from what was actually meant, it really does help you to know a pretty complete picture about it. So I was like, premature optimization of the root of all evil is already an abstraction, and I feel like it was just bad that it was abstracted at some level, and I don't want to add to the problem. Like, I don't actually want to give a new interpretation of the abstraction. I want to just give you the history, and you can make of it what you will. Like, that's just better, in my opinion. Sometimes an abstraction is just harmful because it loses too much of what's actually necessary. And that happened twice in the stuff that we were looking at. Like go-to statement considered harmful was exactly the same way. These are like abstractions of a ton of stuff that was happening in history, and then people argue about it ad infinitum later, but if you just knew what the history was, maybe you could still argue about specifics, but you wouldn't really have to argue about the phrases because there's so much information about what was happening. You can really kind of intuit, it's like, if you want to apply the lessons learned by the things that happened around premature optimizations of all evil, or the things that happened that led to go-to statements that are harmful. It's really easy to know how to apply those when you have all of these concrete examples in history that let you know what led to people thinking these things and what the context really was. So that's it. I'm not giving you any there's no takeaways to talk. The takeaway is the history, or maybe the takeaway is if you do have time and you're inclined and you like some of the things that you heard, please read some computer history. And I'm going to leave the takeaways to the three people that we've been talking about. And I'll give Dijkstra the first one. We'll go in the order that we covered them. He said in one really nice passage that was from personal correspondence with Donald Knuth, he said, "I feel somewhat guilty when I have suggested that the distinction of introduction of different levels of abstraction allow you to think about only one level at a time, ignoring completely the other levels. This is not true. You are trying to organize your thoughts. You are seeking to arrange matters in such a way that you can concentrate on some portion, say with 90% of your conscious thinking, while the rest is temporarily moved away somewhat towards the background of your mind. But that is something quite different from ignoring completely. You allow yourself temporarily to ignore the details, but some overall appreciation of what is supposed to be or to come there continues to play a vital role." Now, Tony Hoare. When he was asked about sort of the sorts of stuff that they did and whether preserving source code was important in an oral history, he said, "It is inconceivable that the first computer I worked on cost in modern currency values £500,000 British pounds, which would be 1 million British pounds today, according to inflation. It worked at 2,000 operations a second, and it had 20,000 bytes of storage. It will be inconceivable how we use these machines just the same way that now we don't know how they built the pyramids." And then finally, for Donald Knuth, when he did his oral history for the Computer History Museum, it was actually an interview by another Turing Award winner, Ed Feigenbaum. And Ed kind of prompted Donald Knuth about this, and he said, "Our current generation and generations of students don't even know the history of their own field. They're constantly reinventing things or thoughtlessly disregarding things. We're not just talking about history going back in time hundreds of years. We're talking about history going back a dozen years or 24 years. And to this, Donald Knuth replies, "I would say that's my major disappointment with my teaching career. I was not able to get this across to any of my students, this love for that kind of scholarship, of reading the source material. I was a complete failure at passing this on to the people that I worked with the most closely. I don't know what I should have done." Thank you very much, everyone. You've been a wonderful audience. Thank you, everyone out there in Twitchland. Thank you. When this VOD goes up, I will try to put references and picture credits up yet. So sorry, that URL won't quite work yet. When the VOD goes up, it will be on there, or maybe I can put it up a little earlier. But I didn't want to spoiler anything. So I will post the picture credits, like the Brian Randell and the Robert McClure photos are really amazing, and I kind of wanted to link to them so that you could go look at the other pictures from the conference if you wanted to. And then I'll put up all the paper links so people can get to them quickly if they want to. Ladies and gentlemen, please welcome to the stage gingerBill, who will be interviewing me, creator of the Odin programming language, and also history aficionado, I believe. So
Yes.
You probably know a lot of these references already.
Yes, luckily. Oh. Oh, wonderful. Well, thank you very much for the talk, Casey. It was absolutely wonderful to read and
Thank you
listen
for
and
listening.
everything. Yes. And I hope everyone in the audience enjoyed it as well, as much as I did. It's that kind of part of history is just stuff I really enjoy reading myself, especially when you brought up the structured programming book. I have that on my bookshelf, and I've read it quite a few times, actually, surprisingly. And I noticed when you were going through the Don Knuth's paper anyway, and going through like examples of Go-To, all of those examples to me, in modern programming languages, we would never even use a Go-To nowadays. We would use break or continue.
Yes.
And that's a for loop. So I don't know if you did any research into that. Did you see like when effectively those constructs happen in programming languages, or was it before then, or just Don Knuth was just showing Go-Tos? I can't remember.
So it's kind of interesting. If you go and read the rest of the paper, it actually makes it more clear. No, he definitely knows about for loops and things like that. But what was happening at that time was sort of, they were trying to like connect, or I should say maybe Donald Knuth was trying to connect the old school structures with the new school structures. And at that time, it wasn't clear that like a for loop was what you needed, or that for loop plus break was what you needed. And so there were all these like competing ideas of what happened, or what should happen. And obviously, this talk was already very long, so I didn't go into this part. But one of the things I found incredibly fascinating, and I highly recommend going and looking at this just for entertainment purposes, if nothing else. But I mean, you're a language designer, so maybe it's more than just entertainment purposes. But it was really fascinating to see the sorts of things they were considering, because while for loops, while loops, those sorts of things they already had and were familiar with, and we are familiar with them, break and continue, maybe not so much. But then there were these other things. For example, there were these ideas of loop and a half, this idea that there would be something like a for loop, but where you had a thing you did before the check as well as after the check. And there were competing proposals for what this loop and a half might look like. And I thought that was pretty interesting, because that is a thing that happens today when I program for loops. I'm like, oh, I really want a construction that says, always do this, like, first go fetch the thing or whatever, and then I want to check, and then I want to do the body. And it's really hard to shoehorn that in, right?
Yes.
And they were acknowledging that even at that time, and like, do we need another one? It turns out, because we now have break and stuff like that, it's like, we just use that instead. But you asked exactly the right question that Knuth was asking too, and so were a lot of other people at that time.
Yeah, because especially since my entire life, I've only known structured programming effectively. So it's just so second nature to me that when I see that and go, but that's just, I see the pattern. Why? And it's just, again, back then, which is not even that long ago. 73 is what? 53 years ago. That's someone's lifetime. In fact, it's still Don Knuth's lifetime.
He's of the three, he is still with us.
Because Tony Hoare just passed away this year. I think it was in March. And then Nicholas Viet, he passed away a couple of years ago on like New Year's Eve, I think it was, or New Year's Day or something like that.
Oh, do you actually know how to pronounce that?
I think it's Niklaus Viet or Nicholas Worth. He used to make the joke that you can pronounce it either way. One's by vowel and one's by name. He was quite a funny Swiss bloke, so
I like
yeah.
that. Okay.
But it was just, I think my pronunciation is correct. If you're Swiss German out there, I apologize.
This is a very multinational conference here, so
Yes.
whenever I'm doing this, I'm like, oh crap, like I'm going to say one of these names so wrong, and there's someone in the audience who knows exactly how it's said, right?
Yeah,
So.
I was also noticing you were doing the Don Knuth things, and you're putting sick next to all of the British spellings.
Yes.
Which is kind of funny for Don Knuth. It's not British, so.
I was kind of wondering that as well.
Yeah.
I'm not sure how that happened, but Because there's some things that are like color or whatever, like LOUR, and or behavior was a big one. Yeah. And so I don't know. That I couldn't say, but I put SIC next to it, so like I didn't Britishize it. It was British.
No, but yes. That's absolutely fine. Now, the question is, I know you did this talk clearly because like people talk about this all on again Twitter, but was that actually the trigger for it? Was the Twitter posts like, maybe I should research more into this, or was it something else in general?
No, the Twitter was just a happy accident that people were talking about the go-to statement part. Because, you know, this talk was based on the premature opposition is the root of all evil one, which I haven't actually seen a Twitter flame war about recently. The go-to considered harmful flame war just kind of happened. I was like, oh, that happens to be something that's part of the story, so I'll go ahead and screenshot that when it came up. But no, like the reason I wanted to do it was just because like it's something that comes up a lot of times in performance. You know, it's often stated, and I just kind of wanted to. I just wanted to know like where it really came from. Like what? Again, it's that feeling of like knowing but not knowing. It's like I didn't really feel like I really understood what it was talking about, and now I feel like I do, at least to that first order. Like in the abstraction hierarchy, right? I'm down to the like what we recorded level. That of course there's always the level of like what actually happened, and only they know that. Right, and maybe they've forgotten it long ago because like the thing about like I'm not sure who said it, right? Like so even they might not really remember what really the truth was, right? But
yeah, which is absolutely fascinating. I'm trying to think more questions. So many. I'm just trying to think which one's better. I'm trying to think. Right, going back to it anyway, with the structured programming, I know it's always these similar people anyway. You keep saying Don Knuth, you've got Tony Hoare, Nicholas Witt, and Dahl. And again, I remember the structured programming book, when I read the section that Dahl did, and Tony Hoare clearly edited, I did find that entire chapter very disappointing, actually. And I don't know if that's what Don Knuth was like. I've got nothing disagreements, because he was like, maybe he didn't understand it. I just found it was literally very explicitly he was talking about similar, not generalized ideas, just because the other parts of the book were very generalized. They did have maybe algo-like syntax in places, but then Dahl's was similar, specifically.
It was odd, and I would imagine that even though I guess you could say in retrospect, it's a very important part because object-oriented programming played such a dominant role in how things went that it like can't be ignored. But at the same time, yeah, like if when I read it today, those first two sections, as you say, are very like relevant. You're just like, okay, like these people could have programmed today, and these things make perfect sense, right? Whereas the Dahl section feels a little bit more like maybe of the time period or something. I don't know, it just doesn't have the same kind of weight to it. But that might also be because I'm not an object-oriented person, right? Like maybe if you really were into those ideas, you'd be like, no, that's the really good part or whatever. So I don't know, that's a good question, and I don't actually know the answer to that. Only Donald Knuth knows whether he understood it completely and was being polite, didn't really understand maybe what the point of it was, or who knows. Donald Knuth was one of the things that I saw when he talked about like his life and his history and his that sort of stuff. One of the things that he said was like he oftentimes didn't buy the BS. Like he would describe times like sitting in an auditorium, like listening to a lecture and being like, what's the point? Like, this is just stupid, right? He was kind of opinionated that way. He wasn't like, and he maybe didn't necessarily confront people about it. Like he wasn't necessarily a troll or anything like that. Like Dijkstra sometimes was, maybe a little bit more to if you listen to people's description of him. But so it's possible that Knuth was just like, I don't see the point of this that much. I'm just going to say a couple things about it because I want to like. It's possible that's happened, but that's just complete speculation. I have no idea, right? Only he knows. So.
One thing I was heavily surprised on when you were dumpster diving, trying to find what all this was, and again, Knuth said it was like 250,000 punch cards that they found and all this lot, and going through all this, and then eventually showing that actually they went through loads of programs and they're all on average very small.
Yes.
Like I've got functions that are bigger than that in my code base.
I mean, everyone does now, right? Yeah.
And I was actually, that's why it was like, I know these computers were limited, but were programs just that small in general? Like effectively they were like, hey, we've bought this general purpose computer and just gone, yeah, we only need to do one thing. And it's...
I'm not really sure because one of the problems is they don't really talk that much about, let me tell you what these programs did. But they do say that they were diverse. Like they kind of gave some examples. We could even, maybe afterwards I'll pull up the paper, we could look at it. But They do give examples of what the programs are, and they are like a diverse set of programs. They weren't like we just looked at like, Slack computing some, physics stuff or whatever, and that's the only thing we looked at. So there were these tiny little math routines that just iterated to solve some, numerical system or something like that. But I really don't know. And the reason that that's kind of weird is because I know these guys did some pretty hardcore stuff, right? They had done algol compilers, they'd done, and Donald Knuth, not that long after, writes Tech, which is a pretty substantial program as well, would almost certainly have stats far in excess of that. The only thing I can think of is it's just at that turning point where for academic and like military use, which is what they were looking at, people just weren't doing it. There were probably people in industry who were like in the software industry who probably had the kinds of programs you're thinking of. And those just didn't enter the survey, which is why I wanted to show those numbers in the talk, because that to me was very important. It's like when he was looking at this and making these sort of assumptions in his head about the source distribution, he's thinking of programs that are very different than anything we do today, and probably very different than a lot of programs at the time if you went to look at different ways of developing software that weren't what they were doing at Stanford and Lockheed. But again, because we don't really have all of the information, I'm very much speculating there.
Yeah, just one thing that came to mind when I was thinking about that speculation was, I remember the TV show in like the end of the series of Mad Men. They were buying a computer.
Yes.
And everyone thought they were crazy to do this. And then I was like, what was he actually computing at the time? Because I actually had to go look and search it. And like, effectively, at the time, the money-making thing was to figure out which time slots were the best to put the adverts in and where to put the advert breaks.
Right.
So it was effectively trying to do linear programming to solve all the best things and just use the simplex algorithm. But then they would have to reprogram it for all the new table stuff and everything like that. But it was effectively just a single-purpose computer which took up probably the size of this stage and just did one program, and it was the money maker because they were trying to optimize for the most amount of revenue because they were an ad company. It's a fictionalized TV show, obviously, with Mad Men, but it was like, that was probably the case back in then. And that's why I was just asking, is it just sole purpose? Because that seemed to be only sole purpose to me. And it was fascinating me. Well, it was just, was that the norm, or did they not realize actually we could use this for everything?
So I don't know, but I mean, in this case, they were sort of using it for everything. It's just all the everythings looked a lot like simplex algorithm sorts of stuff. So it wasn't the simplex algorithm necessarily, it was some other thing. And every department had this thing that they were going to do, but all of those things were fairly small. And I imagine that a lot of that is just because, that software crisis thing that Dyke's just talking about, it's like building larger programs is something only a specialized team can do in those days, right? Only the people who have cracked that nut, right, can actually do it. And so if you're talking about some grad students who are in a completely different discipline even, like they're just doing chemistry research or something like that, they're not going to write something particularly complicated because they're just trying to get their little solver to work and it goes. So it is general purpose, but all the general purposes are fairly, contained. And one of the things too, when they were talking about this sort of stuff, is they like even that picture that they painted where they were talking about we're going to station a person at the computer. So I think the way it was somebody from some department comes in with their stack of punch cards, hands it to the computer operator, right? And they're going to run this thing, and you're going to come back in 30 minutes after they've got it like in and it runs or whatever. One thing that I noticed this is kind of tying it back to the big oops. One thing that I noticed is like one of the reasons Bjarne Stroustrup had to write, I don't know if you remember this from that lecture, he was at Cambridge University, and he's trying to get his simulator thing to work in Simula.
Yes.
And it doesn't work because it takes too long to run, right? And what I found later, I was like rereading some of those papers, I noticed that I kind of missed something. It doesn't change the story at all, but I missed a nice little detail. And that was, later when he's talking about it, he actually says, it probably would have been okay if I'd had more clout. If I was more important, I wasn't just some grad student, but I was like in the chemistry or physics department, like, because remember, computer science is not the big deal at that point, right? If I had more clout, if I was a professor, if I was in one of the physics departments that had the funding and was, important,
Yep.
I might not have had to rewrite it in BCPL because I could have just taken like 3 days of computer time or something to do, right? I could have just demanded that the computer was mine, and I'm just going to run it lots of times with trials and, let it run for excruciatingly long period of time or whatever. And so he kind of was hypothesizing that maybe it would have been okay if he'd had more clout. And so to me, I don't know how, that's what he says. I don't, know the details obviously, but to me that paints this picture of, they had this computer, it was going to be funded by, ARPA gave the funding for this thing, or, so Slack has this computer. There's a pecking order.
Yeah.
You walk in with your slide, with your punch card deck, and if you're important, then you get to take 3 hours of the computer time or something. If you're not, this thing better be done in 30 minutes, and that's kind of what it feels like. So I also think maybe the sizes of programs that they could run might have been limited to look, you're not going to have some continuously running thing that's driving a graphics display. That's not on the table for just the way these things were used. So that's the only other piece of historical context that maybe helps give a,
There's one of the things there's in the stuff they're talking about, the IBM 360. So that was in the 1967 paper you were talking about. And I was surprised that they had that loop cache.
Yes.
And it was 8 double word instructions.
Yes.
Now, I'm going to ask the silly question. What did they mean by a word?
Yeah, you would ask that question, and I don't remember from the paper because it was different for every computer.
Yes, because I remember Don Knuth's, even his first volume, he was talking about a byte, which was 6 bits.
There you go.
Which is why I was asking, what do they mean by a word? Because I know back then they meant word was the smallest addressable space.
Exactly.
Not a byte.
Yeah.
So let's say it could be 16 bits, therefore that was 32 bits. But then it's weird they would call them double words, which I know the Intel Microsoft convention to talk that means like 32 bits nowadays. But I have no idea what that meant, or even if it was big or not, because it could be huge.
It was not huge, but I do not remember the size, right?
Yeah,
it's one of those sizes, it was a 36-bit or whatever,
Yeah.
It's like but they do have, if you're interested in it, that paper is pretty explicit, and they not only talk about sizes like that, but more importantly, probably for what you want to know,
Yes.
is they talk about how the instructions fit in it. So they were how many instructions probably is this that we could fit in these loop caches or whatever. They kind of do that, and it's a little hand wavy because obviously it's not necessarily only a certain amount because much like x86 or something, there's not a defined number of instructions. It's not ARM or something where this is how many instructions will fit. So, but that information is in there, and that paper, I just highlighted the loop cache, but there's all sorts of things like that. The Model 91 was. They were going for it. I don't know what people thought of it since this wasn't a history of the 91.
Yes.
I don't know how well received it was or if these things worked very well. But that is, when I looked through it, I was like, oh man, they were doing it. There's a branch target buffer. It's not, they were not screwing around with the Model 91. Yeah.
Wow, that's impressive.
Yeah.
So I'm going to go to audience questions right now, and let's go. There we go, right on the first row there.
I wanted to ask about algo and how it starts at index 1, and if this is, and in all the languages I use nowadays, I feel like besides Lua, they all start at 0. And I wanted to ask if you know much about the history of programmers being off by 1, and if this is how this kind of thing originated. Is it this kind of thing where it starts out being 1 seems like a reasonable number, and then we're actually 0 is more correct about what we want to do, and stuff like that?
I'm very glad you asked that question, because one of the things obviously, these kinds of talks are very self-indulgent because it's basically me getting to read a bunch of stuff and put in everything that interests me, right? But the downside of that is that it means that I have to cut out a bunch of information that also interests me, right? And one of the things that I cut out was a section on the algol array syntax. It was not one-based per se. It was anything you wanted based. And when I say anything, I mean anything. You could have arrays start at -3 and run through 7, and that was just fine. And not only could you do that, but the syntax inside the array bracket, so when you said, here is how I want to do it, and you want to say, I want it to run from -6 to 12, those things could be limited expressions, meaning the array would get evaluated at runtime. And the expressions could be conditional. So you could be if this value is true, then it starts at -3. But if it's false, I want it to start at 7 times A. And that was just in the, that's not like, oh, some crazy programmer who's just trying to like troll did this. That's in the doc. So if you just go look up like array syntax for the ALGOL language at that time, and you look at the report by Peter Nauer, who wrote it up, it is just straight up, all the crazy things I just said are examples. Like, hey, you could do this. Maybe you should try this, right? So I don't know if this had anything to do with off by 1 error, certainly, but I can tell you that at that time, they were certainly thinking that anything goes for arrays. Like, it is up to you. You can, it's Burger King, not McDonald's. Like, the arrays are your way, and whatever you want to do is fine with us. So
Yeah, and just to add on to that, because I know a bit about ALGOL 68, they do, when you write the array stuff, it will be array, open the square brackets, and it'll be like, say, 0:99, or sometimes it'll be 1:100, right? That, because the thing was, they were inclusive as well, the ranges were, they weren't things. So they already instill instinctively, when you're inclusive, it's 1 indexed. Now, there's a brilliant paper on that by Dijkstra as well, effectively arguing, no, everything should be 0 indexed and exclusive on the maximum range. So it's kind of like, even he was going, can we stop with 1 index, please? 0 index makes mathematics simple, it's less bugs, all of that. Interestingly, I remember when I was starting out early on, I had my colleague at DjangoFX, he was asking me, could we actually add like the variable ranged arrays? Because he had a specific problem he was working on, whereas effectively working in a 3x3 cube, and he wanted to index with -1, 0, and 1 to reference the neighbors. So there's, I kept going, yeah, it's really easy to implement. I could add this in like 20 minutes in the compiler. I kept going, but this is probably going to be a bad idea in the long run. Can we not do this? Can you not just like shift things by 1, please, just so it makes it better for everyone? It was really useful for my specific domain. So I can understand why loads of people want it, because there would be actual cases. And especially when it's dynamic, it would just be, well, we haven't figured out the range yet. Let's just do effectively the variable length array, which everybody hates in like C99 and such. But yeah, right.
I would also point out another thing on top of that, which is that one of the things that I wondered, and I didn't really see an answer for, but because it wasn't, super germane to the talk, I didn't go like try to find more information about it, is I would also think that if you were trying to do stuff like analyze the performance of a program like Knuth was trying to do, or like they were trying to do in that, Stanford study, I would think that looking at source code that's 1-based would also, unless like, and this is why I say I didn't go dumpster diving for this, unless like the 360 kind of already had it set up so that it would be easy to do 1-based addressing or something like that. I was also wondering, like, would that potentially introduce any like extra operations to try and, I got to load this thing from memory, but then it's really kind of wrong because it's, or did that all just come out in the wash? And, like I said, because the talk wasn't really about that, I didn't kind of go down that thing, but it had occurred to me, I was like, because 1-based is not as natural for a computer in ways, to me, like when I think about the assembly language, it's like, unless the computer itself is doing something for you there. So just wanted to add that.
No, thank you. Yeah. Because he did a question to me like, actually, why would they implement it this way? Because always you're going to have to do -1 when you're treating it as an offset.
I'm assuming it's just from the math mind. Like, it's like we wanted to translate mathematical things.
Yes.
I don't know. So.
I've read enough mathematics papers and physics papers, and they're always 1-based.
Yes,
and
exactly.
when they do put a 0 base in, it's like in physics, well, that's time coordinates. We ran out of them. Time. There's only one of them. Put it at 0.
All right.
Right. So, another question. Yes, on the front row.
Did you ever come across where maybe they actually, for the first time, did a kind of like stopwatch-based timing of how long things took? Or if anyone at that time was saying, hey, it would be cool if we could do this kind of thing, maybe?
So because they definitely weren't doing it in the Stanford study, I didn't try to do like a comprehensive analysis of like who were the first people to do that. Do we still have slides on by any chance?
Yeah, we can make it happen. Yeah.
I can show you one thing that they do reference in the Stanford paper. So this is like kind of something that they would have known about because it's directly referenced by Donald Knuth. And let me see. Okay.
Oh, wow.
So this was something I found absolutely fascinating, and it killed me to cut it. So that's why I walked up here and did this. So randomly, because I was, again, dumpster diving, this R. Stockton Gaines thesis from Princeton University it was actually, he calls it debugging, but a lot of the things that they're talking about, they also use the word analysis, which we would now call profiling. He kind of talks about the fact that they're fairly similar things you might want to do. I thought this was absolutely fascinating. This is in 1969, someone doing basically like superluminal or whatever the like kind of graph is. What they did is they took the instruction pointer and they graphed it over time so that it would produce a visual plot of where in your program you were at each cycle count. So as you went through, you can see the loops. It's like I'm doing a bunch of initialization code, then I'm looping, right? I do some other stuff at the end. I come back up looping, right? And you can correlate that you're in the same loop because you're in the same place in memory, right? Because this is memory just going down the side. And like obviously you couldn't really do exactly this today for a number of reasons, one of which being that the program is so huge that it would just be this like mess of crap, but also like getting the IP at that kind of granularity. They had these things at the time that you could literally you could hook up something where it would do it would sort of stream out a magnetic tape of the instruction pointer that you could then feed back in. So you could do that to get this, but the other way that they often did it is just simulated. So I think this one actually comes from a simulated run, not a real run, although I don't really remember for this particular one. But so I didn't find any references in this paper, or I should say this thesis, or in the like sort of the Stanford research everything of people actually doing a stopwatch time, which again, as I think I mentioned in the talk, was kind of weird to me because I would think they would want to know that. But in my head, I just rationalized it as maybe the reason is just because of that sort of the milieu that we talked about at the time. It's like there's an operator who's operating the machine, maybe who puts the punch cards into it, or maybe you do that, and then it's going to like read them all in and do something, and like, would you have to stand there with a stopwatch? Like maybe it didn't have that capability, I don't know. And so, if I would, every time you do one of these things, there's all these things you want to know. And I want to know the same, I want to know that answer, right? And like, so, maybe one of you next year can do the talk that's like the history of profiling, because I would love to know the answer to that. And all I can really do is share with you like this paper, it's gone now, but that paper is a pretty good collection of the things that were commonly done at that time for analysis and debugging. And although like I haven't read the entire thesis because it didn't end up being particularly applicable, so maybe in there somewhere there's someone talking about it, most of the things that you will see don't include a wall clock time for some reason. And it might just be because machines didn't have it, or it might be because they never really thought that was important, and we sort of got that later, that idea that, we should just wall clock time these. I don't really know. And so I'd love it if someone would do that talk, because I'd love to know the answer. And I'm sure we can find it. That's probably something we can find. Yeah. But
Right, finally, the man in the beard.
So when I kind of want to revisit the algol compiler that Tony Hoare was working on, with that went from 100 characters, 1,000 characters to 2. Yeah. Did you do any research onto what the backlash was when they actually published that? Because I imagine if that happened today, that's bankruptcy, right? Mistake.
So I guess I don't remember seeing anything where they talked about the consequences directly to the company. And of course you have to, so let me say two things. I don't want to forget the other one. I'm going to put a pin in it because there's a more direct answer to your question, but I just want to give the setup first. It's important to remember that in this particular case, it was a computer manufacturer. So even if the algol compiler kind of sucks, they already had one and someone else could make an algol compiler if they wanted to. So if they had just been selling software, I bet it would have been a lot worse, right? But because they were a hardware company and what they're making money on is selling the computer and really the software suites that come with it, if we don't have this new software, maybe that doesn't hurt us as much, or it doesn't hurt us as directly. So here's that. In terms of part of the historical record that says what happened there, actually, yes, Tony Hoare does have a pretty direct description of I don't remember, it's the head of sales or somebody gathering the customers together and getting up and announcing so guys, we're not doing any of the software that we said we were going to have. Okay, goodbye. And like he talks about it, and he describes the meeting and everything. So if you do, if you email me after or whatever, I can actually send you a more direct link, like if you want to read about it. But he does describe that. I can't remember. It's probably, I want to say that it's probably in his Turing Award lecture, The Emperor's Old Clothes, but it might not be. It might be in an oral history. So it's in one of those two for sure, though. So it wouldn't take me long to find. Yeah.
Raphael.
Yeah, I'm surprised. Like there were no big programs in that analysis because we know they had them. They had the compilers, for example. Did they not analyze the compilers themselves? And if not, is there a good reason for that? Is it too big to analyze, or is it too in assemblant they couldn't analyze assemblant? Or what prevented them from analyzing the big things they had?
I do not know. Like, I mean, as you saw, it was very difficult for me to kind of make sense of the reference chain of this paper, to the point where I had to like buy the actual physical book because there was such a pause. Like if there had been like a wealth of references and data, you wouldn't have to go chase down one random reference that way, right? And so I don't really understand why the big programs weren't looked at. I mean, there could be reasons for it hidden in the text that I'm forgetting. You know, things like, well, we can't run our analysis tool on it because it's too big. The analysis tool will like choke on things that are that big. It could be something that's more like, well, we just didn't have any at Stanford at the time that were written in Fortran. Because one of the things, so that analyzer only works for Fortran, right? And there were people doing stuff with like an Algol W compiler at that time, where they were going to add some instrumentation to it and stuff like that. That may have gotten written up at some point, I'm not sure, but it would have been after these papers. So it is possible that there were just sort of, I don't know what you want to call them, structural reasons, like sort of impediments to doing it with larger programs that have nothing to do with the fact that they like would have wanted to. Like they may not have been intentionally avoiding those. They might just not have been written in Fortran. Because one of the things is, you know, Fortran, I don't want to speak definitively about it because it's really, I don't know that much about it, but it kind of felt to me like that at the time was really, they wrote things in it that were exactly what it sounds like. They translated mathematical formulas, like formula translator, right, into, you know, code. And it wasn't really necessarily the language of choice for doing something big like a compiler, I got the sense. And I don't know, that could be a completely incorrect sense, but so I think possibly the fact that like, hey, we're trying to take a representative samples of what people are doing out in the real world. Compilers is not really something people are doing out in the real world. Most of our customers, most of the code, you know, I shouldn't say customers, but most of the people who will be downstream of stuff that we do with compiler research, they're doing these Fortran programs, and those aren't compilers typically. They're this other thing. It could have been something more like that, but I'm really just speculating. And part of it too, I'll just say up front, when you do this much, when you try to like cram this much into your brain of the historical record, you start to forget stuff for sure. So it may be, if we went back reading the text for that answer, something that my brain just threw out because it wasn't relative to premature optimization, we could like derive that. So, you know, maybe remind me, and I'll go take another look at the paper to see if I see anything that explains why, you know, why didn't you run on a compiler? They ran it on itself. They literally said, like, we ran this on the Fortran instrumenter and we sped it up. They were like, we self-hosted in a sense the profiler, but I don't remember them talking about a compiler. We should check. We'll check after. Yeah.
Great. You were right there then.
You mentioned that they were kind of thinking that we're going to arrive at the ultimate language maybe at some point.
Yes.
Did you get any insight in what they thought that might be?
So I guess it depends on who you're talking about when you use the word they, because I think each person had their own idea of what that thing would be, as you would expect. These are very opinionated people. You know, programmers are programmers. They would have had Twitter flame wars absolutely if these three guys were on social media. There's no question in my mind. So I can say Donald Knuth actually describes in this go-to paper a number of things that he was thinking would be true about that final language. And if I had to distill it down to like give you an idea of what his idea of where, like roughly where we would be, is he imagined a language where you wrote source code that looked fairly high level, as high a level as you might want to imagine. And it generated like kind of awful code. Like it would generate like just crap assembly language that, would be fine if you were only running this thing once and not on too many things, but you wouldn't care about it otherwise. And then what you would do is you, the programmer, would pick the transformations you wanted to have happen. Like he imagined a world where he'd say, unroll that by 4, hoist that outside the loop. So in his mind, because I think he was very focused on efficiency at that time and things like that, he was thinking about those things, and now like analysis of algorithms is all about like runtimes and stuff too, right? So he's very much in that. He hasn't written tech yet, so he's not thinking big programs. Like maybe he hasn't quite put himself in the mental space of the things that are important for that. So he was kind of thinking like the ultimate programming language is the one where I just sketch out what I want, it generates bad code, then I just like add these transformations to it, and those are like non-destructive. So I still have the original thing, I could go modify it, and it would apply the transformations again if they were applicable, or I'd redo the transformers if they're not applicable. I think if you were to give him something like LLVM, he might, and obviously not today, but back then, I think he would probably think that was pretty good. Like it's heuristically doing those transformations for me when I say -03. And then he probably also, like many people today, would be annoyed when like it did the wrong thing. When he looked at it, it was like, that's not what I wanted, and I would have liked to have been able to control this, right? But I think he got some of what he wanted, but maybe he didn't get the amount of control that he would have liked, because all of those sorts of like optimization choices are kind of considered outside the language in a lot of languages, and I think he envisioned a world where they were inside it. Yeah, that's my best guess at what it would be. And like I said, if you really want to know, you can read the go-to paper, and there's a lot of sections where he kind of imagines a future language.
Yeah, it's kind of, if that was the case, it's kind of like, you would have probably hated LLVM because you're forced to have certain passes in certain orders as well. Like they are literally, you have to do this pass first, then you have to do the others. You can't mix and match when you want it. But again, LLVM is pretty much the only one that's open source and like available for most people to use. So if they want anything else, they'll have to implement themselves. But yeah, it is. And again, I remember you were reading the sources. You're reading from Tony Hoare, him effectively inventing SSA.
Oh yeah,
Yes.
That's not in the talk, but yeah.
I remember you were seeing this, and it's like 15 years before it was actually invented.
Yep.
And it was like, oh, he's just described the entire thing here.
Yeah, that was weird, and
Yes.
there was no place for it in the talk, but it was cool. One of the things that I feel like is super cool about reading the history like directly is that, not to badmouth my own talk, but if you go watch someone's talk on it, you get what was interesting to them. If you go read it yourself, you find all these things that might be interesting to you that weren't interesting to them, because they're all over the place, right? And that was an example of that, right? Didn't make the talk, but super interesting part. And there's lots of stuff like that where you're like, oh man, they were thinking about this thing at the time that, I would have thought no one would have been talking about till the 80s or something, right? But not true.
No.
So.
Right. Ryan.
So it was pretty interesting to hear the references to like the software crisis and the software problem by like different people. And I was curious if you came across any information about I guess my understanding of that from your talk, and this might be wrong, is that was about like hardware becoming more capable and software becoming more complex. So that's what the structured programming constructs were for, presumably.
Yes.
Did you come across any information about how their feelings about the crisis evolved? Like, did they think that this solved it, or did they think that it led to other problems, or like, was there any information about? I'm curious how their feelings changed over time.
So you're talking about basically like post 1974.
Yeah.
Okay. So I guess what I would say is for Donald Knuth specifically, I don't really know, because I didn't again, I kind of have to keep it manageable for me, so I kind of I stop after we the thing we're looking at. So I didn't look at like how did Donald Knuth like change his mind over time if he did on things. So for Knuth, I couldn't really say. For Tony Hoare and Edsger Dijkstra, I would say kind of you do find out a little bit about that, just even when you're only just looking at these things. It kind of seems to me like they really had an underlying feeling that programs should have more mathematical definitions to them. And while I'm sure they would say that the change to what we now consider structured programming, or what we now consider programming, but then they call it structured programming, I'm sure they considered it an improvement, but I think it kind of felt like they were always chasing this notion of surely there must be some way to guarantee that these programs are more correct, right? And so I think that if they were to, one thing I would say is, although obviously like I love reading about all this stuff and like I feel like these people were obviously incredible at what they did, when I think about like what I do for programming or how I like to think about programming, it's very far from any way that they ever think about it. Like they are clearly thinking about it very differently. To the point where I would say like Dijkstra, for example, I would say thinks about programming almost like completely opposite to how I might think about it. I believe I read in his oral history him talking about, I hope I'm not misattributing this, but I believe he was one who was saying like, he was talking admirably about a company that was basically like, look, if you have like a 9-month project, then 6 months of that, you should not be doing any programming. You should just be like planning what you're gonna do. And then once the plan is complete and you only have like 3 months left, then you can write some code, right? And so, I can't even like imagine how that doesn't seem like it will work at all, except for like very, very simple problems. But that's not how he thought about it, right? And so to try and imagine what his reaction would be, other than to just look and go in those oral histories, he'll say things like that, right? And he'll talk about how there's a lot of really crappy software still and all this. So he obviously wasn't psyched, but I guess what I would say is he probably was happy enough, but always felt like that it should have been, maybe to him it was always math. Like it's always like it should be more formal than this, it should be more provable than this. And so I imagine it's probably not hard to guess that he would still be kind of grumpy about it today, right?
Good.
Probably a safe bet.
Good. Well, thank you very much for all the questions, and please, for one more time, please give a round of applause to the great Muratori.
Thank you, Bill. That was lovely.
Thank you very much.